Imagine a time before the universe had color. No vibrant nebulae, no dazzling galaxies, just a vast expanse of primordial darkness. The first stars ignited like cosmic torches, but they were simple, made only of hydrogen and helium, the two lightest elements. They burned hot, lived fast, and died young, leaving behind nothing but black holes and raw energy. But then something changed. A second generation of stars emerged, and with them came a revolution that shaped everything we see in the universe today, including us. These were the population 2 stars, the silent architects of galactic evolution, the stars that took the universe from a bland void to the breathtaking cosmic tapestry we now struggle to comprehend. Without them, the elements that make up planets, moons, and even the molecules in your body wouldn't exist. But what exactly were these stars? How did they differ from the ones before them? And why do astronomers obsess over them, believing they hold the key to unlocking the deepest secrets of the cosmos? To understand the role of population 2 stars, we have to rewind to a time before the Milky Way was even recognizable. Back when galaxies were still assembling themselves, gas clouds were collapsing, and chaos reigned in the young universe. Population 2 stars were born into this mess, forming from slightly enriched clouds of gas that had been touched by the remnants of the very first stars, known as population 3. These earlier stars had only hydrogen and helium to work with, meaning they lacked the heavier elements that allow stars to form planets or create complex chemistry. But when population 3 stars exploded in titanic supernovae, they seeded the universe with the first traces of heavier elements: carbon, oxygen, iron, and more. These materials mixed into the surrounding gas clouds, and when those clouds collapsed again, they gave birth to a new kind of star. These were population 2 stars, still mostly hydrogen and helium, but now with just enough heavier elements, what astronomers call metals, to change the game completely. The first thing that set population 2 stars apart was how they lived. Unlike their predecessors, which were enormous and short-lived, many population 2 stars were slightly smaller and burned for much longer. Some of them are still around today, surviving for billions of years. If we find these ancient stars and analyze their chemical makeup, we can essentially look back in time, peering into the earliest eras of galaxy formation. But population 2 stars weren't just passive observers of cosmic history. They were the engines that drove the next big transformation in the universe. As they aged and died, they produced even more heavy elements. Some of them ended in supernova explosions, sending metals flying into space, enriching the next generation of star-forming clouds. Others evolved into red giants, gently releasing their outer layers into the cosmos, further spreading the essential ingredients for planets, moons, and eventually life itself. Without population 2 stars, the Milky Way wouldn't exist in the form we see today. They were responsible for shaping early galaxies, pulling in surrounding gas with their gravity, triggering new waves of star formation, and helping carve out the grand spiral structures we now admire in deep space images. And here's where things get really interesting. Some of the oldest population 2 stars are found in a specific type of celestial structure, globular clusters. These clusters are dense, ancient groups of stars that orbit galaxies like the Milky Way, and they're some of the best places to find population 2 stars that have remained largely unchanged for billions of years. By studying these stars, scientists can decode the history of our galaxy, tracing back how it formed and evolved over time. Some of these stars are so old that they date back to when the universe was less than 1 billion years old, meaning they carry the secrets of an era we can never directly observe. But the most mind-blowing part: population 2 stars were the bridge between the first lifeless stars and the complex, element-rich cosmos we live in today. Without them, there would be no population 1 stars, the ones that contain even more metals and are capable of forming planets like Earth. In other words, if population 2 stars never existed, either would we. And yet, despite their importance, there are still mysteries surrounding them. Scientists are still trying to figure out exactly how the transition from population 3 to population 2 happened, how much heavier material these stars could produce, and whether there are any ultra-metal-poor stars that might be even older than we think. Astronomers are constantly on the hunt for new clues, using telescopes like the James Webb Space Telescope to peer deeper into the universe and uncover faint, distant stars that might be relics from this crucial period in cosmic history. But one thing is certain: Population 2 stars were the architects of the universe as we know it. They took a lifeless cosmos and turned it into one teeming with possibilities. They were the first step toward planets, toward chemistry, and ultimately toward life. And the more we learn about them, the more we realize just how interconnected everything in the universe truly is. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it exists because of the ancient stars that came before us. The story of Population 2 stars isn't just a scientific one. It's a story of transformation, of rebirth, and of the relentless march of time. The universe is constantly evolving, reshaping itself, and the stars that came before us set the stage for everything we see today. And yet, the story isn't over. There are still mysteries to solve, secrets waiting to be uncovered in the oldest stars in the galaxy. What else can they teach us? What hidden knowledge do they hold about the earliest days of the cosmos? As we push further into the unknown, one thing remains clear: if we want to understand where we came from, we have to look to the stars that came before us. Because in the end, their story is our story, written in the light of ancient suns that burned long before Earth even existed. Population 2 stars were more than just the missing link between the first and third generations of stars. They were the great cosmic recyclers, turning the raw materials left behind by Population 3 stars into something entirely new. Every single one of them played a crucial role in reshaping the galaxies around them, injecting the cosmos with the first hints of complexity that would eventually lead to planets, chemistry, and life itself. But how exactly did they do it? To fully grasp the impact of Population 2 stars, we need to understand their life cycles. Unlike their massive and short-lived predecessors, many Population 2 stars were smaller, allowing them to burn through their fuel much more slowly. This meant that while the biggest ones still ended their lives in dramatic supernova explosions, many others followed a much more gradual path, swelling into red giants before gently shedding their outer layers into space. This slow and steady process of stellar evolution was critical because it allowed heavy elements to be dispersed into the interstellar medium over time. The elements released by Population 2 stars, carbon, oxygen, silicon, iron, were the first true building blocks of complex cosmic structures. These materials mixed with the surrounding gas clouds, enriching them just enough to allow for the birth of even more chemically diverse stars. The impact of this gradual enrichment cannot be overstated. Before Population 2 stars, the universe was nearly devoid of anything heavier than helium. But as these stars lived and died, they steadily increased the concentration of metals in the cosmos. This paved the way for the emergence of Population 1 stars, the most metal-rich stars, which include our own Sun. The reason this metal enrichment was so important comes down to how stars and planets form. Hydrogen and helium alone aren't enough to create the complex chemistry needed for planets like Earth. It takes heavier elements like carbon to form organic molecules, silicon to build rocky planets, and iron to create planetary cores. Without Population 2 stars enriching the universe with these elements, there would be no planets, no oceans, and no living organisms. But here's where things get even more fascinating. Some of the oldest known Population 2 stars are found in the halo of the Milky Way, orbiting the galaxy in vast, slow-moving paths that suggest they were among the first to form. Many of these stars exist within globular clusters, dense, ancient spheres of stars that predate the Milky Way's spiral structure. These globular clusters are like cosmic time capsules, containing stars that have remained largely unchanged for billions of years. By studying their compositions, astronomers can piece together a timeline of galactic evolution, tracing how the Milky Way gradually built itself up over time. Some of these clusters contain stars that are nearly as old as the universe itself, meaning they hold clues about the very earliest epochs of cosmic history. But there's another mystery surrounding Population 2 stars that still baffles astronomers. While we've identified many of them, we haven't yet found the perfect missing link between them and their Population 3 predecessors. The oldest Population 2 stars are still more chemically enriched than we would expect if they had formed directly from Population 3 supernova remnants. This suggests there might have been an intermediate step in the chemical evolution of the universe, one we have yet to discover. One of the most exciting areas of modern astrophysics is the hunt for ultra-metal-poor stars, population 2 stars with the lowest possible concentrations of heavy elements. These stars are rare, but they act as crucial data points in our understanding of cosmic history. If we can find one that has an almost pure hydrogen-helium composition, it might provide the closest look we'll ever get at the very first chemical processes that occurred after the Big Bang. The James Webb Space Telescope has already begun to provide deeper insights into the era of population 2 stars, allowing astronomers to look farther back in time than ever before. By studying ancient galaxies and their stellar populations, scientists hope to pinpoint exactly when and how the transition from population 3 to population 2 occurred. But why does this matter? Why should we care about stars that burned out billions of years ago? Because their story is our story. Every atom in your body, every molecule in the air you breathe, was once inside a star. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it was forged in the heart of an ancient star and scattered into space when that star died. When population 2 stars began to spread these materials across the cosmos, they unknowingly set in motion the events that would lead to planets, to chemistry, and ultimately to us. In a way, we are made of the universe's second draft, the improved version of what came before. If the first stars were the rough outlines of a cosmic blueprint, then population 2 stars were the editors, refining and reshaping the universe into something more dynamic, more complex, more alive. And yet, for all we've learned, the story of population 2 stars is still unfolding. There are still countless questions to answer, countless stars to study, and countless mysteries waiting to be unraveled in the depths of space. The more we learn about these ancient stars, the more we understand the fundamental processes that shaped everything we know. And in doing so, we get closer to answering some of the biggest questions of all. Where did we come from? How did the universe become what it is today? And what other cosmic secrets are still waiting to be discovered? The search for answers about population 2 stars has led scientists to some of the oldest and most mysterious corners of the universe. These stars, despite being ancient relics, continue to play a crucial role in modern astrophysics. By studying them, we not only gain insight into the past but also refine our understanding of how galaxies, including our own Milky Way, evolved over billions of years. One of the most compelling aspects of population 2 stars is their presence in the galactic halo. Unlike the bright, young stars that form the spiral arms of the Milky Way, halo stars orbit in vast, elliptical paths that take them far above and below the galactic plane. These stars move in a way that suggests they formed before the Milky Way's disk fully developed, meaning they offer a direct look at the early stages of our galaxy's formation. The chemical composition of these stars tells a fascinating story. Compared to younger population 1 stars, which are rich in heavy elements, population 2 stars are far more metal-poor. This is because they formed at a time when the universe was still transitioning from the pure hydrogen-helium mix left by the Big Bang to a more complex chemical landscape. However, the fact that they contain some heavier elements proves that at least one generation of stars, population 3, had already lived and died before them. But here's where things get strange. While we have a good understanding of how stars evolved today, the earliest stages of star formation in the universe remain one of the biggest cosmic mysteries. Theoretical models suggest that population 3 stars were massive and burned through their fuel incredibly quickly, exploding in supernovae that seeded the cosmos with its first batch of heavy elements. However, we have yet to directly observe a population 3 star or even find a direct remnant of one. This is why astronomers are so interested in finding the most metal per population 2 stars. The less metal a star has, the closer it is to that first generation, and the more it can tell us about how the universe transitioned from an almost featureless void into the structured, complex cosmos we see today. Some of the most metal-poor stars ever discovered reside in the Milky Way's halo, and in distant dwarf galaxies orbiting our own. These small galaxies are like fossils, preserving the chemical makeup of the early universe with minimal contamination from later stellar generations. Studying them allows astronomers to trace back the history of element formation and understand how the Milky Way grew over time. But there's another side to this story, one that challenges our assumptions about how galaxies formed in the first place. The discovery of extremely metal-poor stars in the halo suggests that the Milky Way may have undergone a more chaotic and violent formation than we once thought. Instead of forming smoothly from a single cloud of gas, it appears that our galaxy built itself up by merging with smaller proto-galaxies, absorbing their stars and enriching its chemical makeup along the way. This hierarchical formation model, supported by both observations and simulations, suggests that many of the population 2 stars in the halo were not born in the Milky Way at all. Instead, they may have originated in smaller galaxies that were later devoured by our own, their stars scattered into wide, looping orbits that now formed the halo. This would mean that some of the oldest stars in our galaxy are actually immigrants, remnants of ancient, long-lost galaxies that were torn apart by the Milky Way's gravity billions of years ago. This realization has led to a growing effort to map the movement of these stars, tracing their origins and uncovering the history of galactic mergers that shaped the Milky Way into what we see today. One of the most important tools for this research has been the Gaia spacecraft, which has provided an unprecedented map of the positions and motions of billions of stars in the Milky Way. By analyzing how population 2 stars move through the galaxy, astronomers can identify distinct streams, rivers of stars that were once part of separate galaxies before being absorbed by the Milky Way. These discoveries suggest that the early universe was far more dynamic than we ever imagined. Instead of stars forming in isolated pockets, it seems that galaxies were constantly colliding, merging, and exchanging material, creating a chaotic but incredibly productive environment for stellar evolution. And yet, despite all we've learned, there's still an enormous gap in our understanding. We know that population 2 stars played a crucial role in enriching the universe, but we still don't fully understand the details of this process. What were the exact mechanisms that determined how heavy elements were distributed? Why do some regions of the universe seem to have formed stars at a much slower pace than others? Some scientists believe that magnetic fields may have played a key role in shaping the evolution of population 2 stars. Magnetic fields can influence how gas clouds collapse into stars, potentially explaining why some parts of the early universe formed stars more efficiently than others. This is an area of active research, with new observations and simulations constantly refining our models. Another unsolved mystery is the role of dark matter in this process. While we can't see dark matter directly, we know it makes up a significant portion of the universe's mass. Some theories suggest that dark matter may have influenced the formation of the first galaxies, providing the gravitational scaffolding that allowed population 2 stars to form in the first place. If this is true, then understanding population 2 stars isn't just about learning how the universe evolved. It could also help us unlock the nature of dark matter itself. As we continue to push the boundaries of astronomical observation, new telescopes like the James Webb Space Telescope will allow us to peer deeper into the early universe than ever before. With its advanced infrared capabilities, Webb is capable of detecting some of the oldest and faintest galaxies, potentially revealing new clues about the transition from population 3 to population 2 stars. And who knows what else we might discover? Every time we think we've answered one cosmic mystery, we uncover another. The deeper we look into the past, the more we realize how much we still don't understand. But that's the beauty of space exploration. The universe is a vast and ever-unfolding puzzle, and every new piece we find brings us closer to understanding the grand story of how everything, including us, came to be. The hunt for the oldest population 2 stars continues to challenge our understanding of the early universe. These stars, which bridge the gap between the first primordial stars and the rich, metal-laden stars we see today, hold secrets that could reshape how we think about cosmic evolution. Every discovery in this field adds a new layer of complexity, revealing that the universe's past was far from simple or predictable. One of the biggest surprises about population 2 stars is that they are not all uniform in their metal content. While they are generally metal-poor compared to younger stars, some of them contain slightly higher amounts of heavy elements than expected. This suggests that not all population 2 stars formed at the same time or in the same environment. Some must have formed after multiple waves of supernovae had already enriched their surroundings with heavier elements. Others might have been born in isolated pockets of the universe, where metal enrichment was slower. This variation is particularly noticeable in globular clusters, dense, spherical groups of stars that orbit the Milky Way. These clusters contain some of the oldest known population II stars, yet even within a single cluster, there can be differences in chemical composition. This is strange because globular clusters were once thought to form all their stars in a single burst, meaning they should all have the same chemical fingerprint. But instead, we see evidence of multiple generations of stars within these clusters, suggesting that some of them managed to form new stars even after their first generation had already lived and died. This discovery raises new questions. How did some globular clusters manage to hold onto the material from earlier generations of stars, while others did not? Could the most ancient clusters have been the remnants of even older, long-lost dwarf galaxies that were stripped of their outer stars and absorbed into the Milky Way? Some astronomers believe that studying the most metal-poor stars in these clusters could provide an answer. But globular clusters are not the only places where population II stars hold surprises. In recent years, astronomers have discovered that some of these stars are moving at incredible speeds, fast enough to eventually escape the Milky Way entirely. These so-called hypervelocity stars are thought to have been ejected by powerful gravitational interactions, either from supermassive black holes or from interactions with other stars in dense stellar environments. The fact that some of these high-speed stars are ancient population II stars adds another layer of mystery. Where did these stars originally come from? If they were part of an ancient galactic collision, could they be remnants of long-lost galaxies that merged with the Milky Way billions of years ago? Some hypervelocity stars appear to be traveling in directions that suggest they originated in the galactic halo, further supporting the idea that our galaxy has absorbed many smaller galaxies over time. This leads to another fascinating aspect of population II stars: their role in galactic archaeology. By studying the motion and chemical composition of these stars, astronomers can reconstruct the history of the Milky Way, tracing back when and how it absorbed other galaxies. In some cases, entire streams of stars have been identified as remnants of ancient galactic mergers, stretching across the sky in long, ghostly trails. One of the most famous examples of this is the Gaia-Enceladus merger, a cosmic collision that took place around 8 to 10 billion years ago. This event is believed to have brought a significant number of population II stars into the Milky Way, mixing their metal-poor material with the existing stellar population. Many of the stars that now make up the galactic halo are thought to be remnants of this merger. But what about population II stars in other galaxies? Do they follow the same patterns as those in the Milky Way? Observations of nearby galaxies like Andromeda and various dwarf galaxies suggest that the processes at work in our galaxy are not unique. Other galaxies also show evidence of past mergers, disrupted stellar streams, and metal-poor stars tracing the footprints of ancient cosmic interactions. One of the most exciting prospects for future research is studying population II stars in extremely distant galaxies. These galaxies, seen as they were billions of years ago, could provide direct insight into the transition from the first stars to the enriched universe we see today. The James Webb Space Telescope has already begun detecting some of the most distant galaxies ever observed, and with its powerful infrared instruments, it may soon allow astronomers to study the chemical makeup of population II stars in those early galaxies. If we can pinpoint exactly when and how these stars formed, we may finally be able to answer one of the biggest questions in cosmology. How did the first heavy elements spread throughout the universe, setting the stage for everything that followed? Another mystery tied to population II stars is the nature of their remnants. Many of these ancient stars have already reached the end of their life cycles, but where are their remains? Some likely ended their lives as white dwarfs, slowly cooling over billions of years. Others would have exploded in supernovae, seeding the cosmos with heavier elements. But could some population II stars have collapsed directly into black holes? If so, this could have major implications for our understanding of black hole formation. The first generations of stellar black holes, formed from population III and early population II stars, could have merged over time, growing into the supermassive black holes we see at the centers of galaxies today. This idea is still being explored, but if true, it would mean that population II stars played a key role not just in enriching the universe but in shaping the structure of galaxies themselves. As technology advances, new telescopes and observational techniques will continue to push the boundaries of what we can learn about these ancient stars. With each new discovery, we refine our understanding of the cosmic timeline, piecing together how the universe evolved from a sea of hydrogen and helium into the diverse and complex cosmos we see today. And yet, even with all we've learned, the story of population II stars is far from complete. There are still many unanswered questions, lingering mysteries that challenge our understanding of stellar evolution and galactic formation. The deeper we look, the more we realize that the universe is an ever-unfolding puzzle, full of secrets waiting to be uncovered. One of the biggest challenges in studying population II stars is identifying the oldest and most pristine among them. While we know these stars contain traces of heavier elements, pinpointing which ones formed earliest requires incredibly precise measurements. Astronomers rely on spectroscopy, the study of light emitted or absorbed by objects, to analyze the chemical fingerprints of these stars. By measuring the abundance of elements like iron, carbon, and oxygen, scientists can estimate a star's age and determine how much it has been influenced by past generations of supernovae. But here's where things get tricky. Not all population II stars have the same levels of metal enrichment. Some, known as extremely metal-poor stars, contain only tiny traces of heavier elements, suggesting they formed from material that had barely been touched by earlier supernovae. These stars are the closest living relatives to the very first stars, and studying them is like reading a history book written in the language of chemistry. One such example is a star known as SMSSJ 031300.36-670839.3, located in the Milky Way's halo. This star has one of the lowest iron abundances ever detected, meaning it likely formed from the remnants of just one or two early supernovae. Studying stars like this helps astronomers reconstruct the conditions of the early universe, showing how the first heavy elements were produced and distributed. But what about population II stars outside our galaxy? The most ancient stars aren't just found in the Milky Way, they exist in other galaxies too. In nearby dwarf galaxies, astronomers have identified stars with similarly low metal content, suggesting that these galaxies have preserved ancient stellar populations that remain largely unchanged since the early universe. One of the most intriguing discoveries in this field came from the Sculptor Dwarf Galaxy, a small satellite of the Milky Way. Some of its oldest stars have chemical signatures remarkably similar to those found in the halo of our galaxy, reinforcing the idea that many of the Milky Way's oldest stars originally belonged to smaller galaxies that were later absorbed. This process of galactic cannibalism, where larger galaxies consume smaller ones, has played a major role in shaping the universe as we see it today. But how do population II stars contribute to this cosmic cycle? Their role isn't just passive. They actively shape the evolution of galaxies by enriching their surroundings with heavy elements. When a population II star reaches the end of its life, it either explodes in a supernova or sheds its outer layers in a less violent process. Either way, it releases heavier elements back into space, where they mix with surrounding gas clouds. Over time, these enriched clouds form new generations of stars, each with progressively higher metal content. This gradual buildup of elements is what allows planets, moons, and even life to exist. If population II stars hadn't seeded the universe with oxygen, carbon, and iron, planets like Earth would never have formed. Every atom of gold, silver, and platinum in the universe was forged in the explosions of ancient stars, scattered across space, and later incorporated into new celestial bodies. But not all population II stars followed this typical evolutionary path. Some ended their lives in ways that remain mysterious. For example, certain ancient stars appear to have exploded in supernovae that left behind no trace of a neutron star or black hole. This suggests that some early supernovae were far more efficient at dispersing their material than modern ones. Understanding why these early explosions behaved differently is an ongoing puzzle in astrophysics. Another mystery lies in the relationship between population 2 stars and dark matter. While we can observe stars directly, dark matter remains invisible. It doesn't emit or absorb light, yet it exerts a gravitational influence on galaxies. Some astronomers believe that the distribution of population 2 stars in the halo of the Milky Way could provide clues about how dark matter is spread throughout the galaxy. If we can map the motions of these ancient stars, we might be able to indirectly detect the presence of dark matter, revealing its role in galactic formation. One particularly interesting idea is that some population 2 stars may have been born in regions where dark matter was especially dense. If true, this could explain why certain old stars are found in unexpected locations, moving in strange orbits that don't align with the rest of the Milky Way's stellar population. By studying these stars, scientists might be able to uncover new details about the structure of dark matter and its role in shaping the early universe. And then there's the question of population 2 stars and globular clusters. These ancient star clusters, which orbit the Milky Way in the galactic halo, are home to some of the oldest known stars. But recent studies have shown that many globular clusters contain stars with different chemical compositions, suggesting that multiple generations of stars formed within them. This contradicts earlier theories that all the stars in a globular cluster formed at the same time. Some astronomers believe that certain globular clusters might actually be the remnants of ancient dwarf galaxies that were stripped of their outer stars and absorbed into the Milky Way. If this is true, then studying these clusters could provide valuable insights into how galaxies merge and evolve over time. Another open question is whether any population 2 stars have survived in near-pristine form, completely untouched by later generations of supernovae. If we could find a star that contains absolutely no elements heavier than hydrogen and helium, it would be the closest thing we have to a direct remnant of the universe's first few billion years. Some astronomers believe such stars might exist in the far reaches of the Milky Way's halo, or even in isolated regions of intergalactic space. The search for these ultra-primitive stars is ongoing, with telescopes like the Very Large Telescope, VLT, and the upcoming Extremely Large Telescope, ELT, helping to push the boundaries of what we can detect. Future discoveries could provide unprecedented insights into how the first generations of stars shaped the cosmos, answering questions that have puzzled scientists for decades. As we continue to study population 2 stars, one thing becomes increasingly clear. The universe is far more interconnected than we ever imagined. The stars we see in the night sky are not isolated points of light. They are part of a vast cosmic story that stretches back to the dawn of time. Each ancient star we study brings us one step closer to understanding how the universe evolved from a sea of hydrogen and helium into the complex, structured cosmos we see today. And yet, despite all we've learned, the story is far from over. There are still countless mysteries waiting to be uncovered, hidden in the faint glow of distant stars, encoded in the chemical fingerprints of ancient supernovae, and written in the motions of galaxies that have been colliding and merging for billions of years. The deeper we look, the more we realize how much there is left to discover. So as we continue our journey through the cosmos, let's remember that the universe is not just something we observe, it's something we are a part of. The atoms in our bodies, the elements in our planets, and the stars that light up the sky all share a common origin. And by studying the ancient stars that came before us, we gain a deeper understanding of our own place in the grand cosmic story. The deeper we explore the role of population 2 stars in galactic evolution, the more we uncover about the intricate web of processes that shape the universe. One of the most compelling aspects of these ancient stars is how they provided the raw material for the formation of population 1 stars, the younger, metal-rich stars that dominate galaxies today, including our own Sun. But to fully understand how population 2 stars contributed to this transition, we need to examine the precise mechanisms by which they enriched the cosmos with heavier elements. When these stars reached the end of their lifetimes, many of them exploded as Type II supernovae, powerful stellar explosions that dispersed elements such as carbon, oxygen, and iron into the surrounding interstellar medium. These supernovae not only seeded galaxies with new elements, but also triggered the formation of new generations of stars by compressing nearby gas clouds. However, not all population 2 stars ended their lives in the same way. Some, particularly those with lower masses, evolved into white dwarfs, cooling remnants of stars that no longer undergo nuclear fusion. Over billions of years, these white dwarfs gradually fade, but they also play a crucial role in galactic chemical evolution. When a white dwarf is part of a binary system, where two stars orbit each other, it can accumulate material from its companion. If it gains enough mass, it can explode in a type Ia supernova, which produces a different mix of elements compared to a core collapse supernova. These different types of supernovae created distinct chemical signatures throughout the universe. By analyzing the elemental composition of stars and gas clouds, astronomers can trace the contributions of various stellar explosions to the formation of later generations of stars. This is why studying population II stars is so important. They serve as cosmic time capsules that allow us to reconstruct the chemical history of the universe. Another fascinating consequence of population II stars is their role in galaxy formation itself. In the early universe, small protogalaxies, dense regions of gas and dark matter, formed the building blocks of modern galaxies. These protogalaxies contained population II stars that helped shape their structure. The energy released by early supernovae likely played a crucial role in determining whether a protogalaxy would grow into a massive system like the Milky Way or remain a small, isolated dwarf galaxy. This process, known as feedback, is one of the most important mechanisms in galaxy evolution. When population II stars exploded, they generated powerful shockwaves that either compressed gas clouds, triggering new star formation, or blew material out of the galaxy, limiting its growth. The balance between these opposing effects determined how galaxies evolved over billions of years. One of the biggest mysteries in astronomy is how early galaxies accumulated enough heavy elements to form stars like our Sun. The answer lies in the repeated cycles of star birth and death driven by population II stars. Each generation of stars added more heavy elements to the universe, gradually enriching the gas clouds that would later collapse into new stars and planetary systems. But there's another aspect to consider: the movement of population II stars. Unlike the orderly orbits of younger stars in the Milky Way's disk, these ancient stars often follow highly elliptical, or even chaotic trajectories, hinting at a more turbulent past. Many of them reside in the galactic halo, a vast, diffuse region surrounding the Milky Way that extends far beyond the visible disk. This distribution suggests that population II stars formed in a very different environment compared to today's stars. Some of them likely originated in small satellite galaxies that were later absorbed by the Milky Way through gravitational interactions. This process, known as hierarchical galaxy formation, is a fundamental aspect of how large galaxies like ours grew over time. One of the strongest pieces of evidence for this idea comes from stellar streams, long, thin trails of stars that trace the remnants of smaller galaxies torn apart by the Milky Way's gravity. Many of the stars in these streams belong to population II, further confirming that our galaxy has been shaped by a history of mergers and acquisitions. But there's still a major question: are there any population II stars that are truly isolated, untouched by later cosmic events? Some astronomers believe that the answer might lie in the outskirts of the Milky Way, where some of the oldest and least disturbed stars could still exist. Finding such stars would be like uncovering fossils from the earliest days of the universe, providing an even clearer picture of how the first galaxies evolved. To search for these ancient stars, astronomers use high-resolution spectroscopic surveys, such as the Gaia mission, which maps the positions and motions of billions of stars. By identifying stars with extremely low metal content, scientists can pinpoint the ones that formed earliest in cosmic history. Recent discoveries suggest that some of the oldest known stars are more than 13 billion years old, meaning they formed shortly after the Big Bang. This leads to an even more profound question: could any of these ancient stars still have planets? While we typically associate planets with metal-rich stars like the Sun, there is growing evidence that some population II stars could host planetary systems. If this is true, then it raises the possibility that rocky planets, perhaps even habitable ones, could have existed far earlier in the universe than we previously thought. Of course, the chances of life developing around a metal poor star would be much lower than around a star like the Sun, simply because the necessary ingredients for complex chemistry might not have been present in sufficient quantities. But even if these ancient planets were barren, their existence would challenge our understanding of planetary formation and the conditions necessary for life. As we continue to study population 2 stars, we are not just learning about the history of the universe. We are also uncovering the foundations of everything we see today. These stars serve as the missing link between the first stars that illuminated the cosmos and the familiar galaxies, planets, and stars that exist now. Their light carries the story of how the universe evolved, piece by piece, from a chaotic sea of hydrogen to the structured, element-rich cosmos we observe. The search for the oldest stars is far from over. With next-generation telescopes like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, we will be able to peer even deeper into space and time, identifying stars and galaxies that formed in the universe's earliest epochs. These discoveries will refine our understanding of cosmic history, allowing us to fill in the gaps in our knowledge of how the first heavy elements were produced, how galaxies grew, and how the universe became what it is today. And yet, despite all we've learned, there are still unanswered questions. Are there undiscovered classes of ancient stars lurking in the shadows? Could some population 2 stars have formed in ways we don't yet understand? And most intriguingly, could the oldest stars in the universe still be out there, waiting to be found? As long as these questions remain, the study of population 2 stars will continue to push the boundaries of our knowledge. These ancient stars are not just relics of the past. They are the key to understanding how the universe came to be. Every discovery brings us one step closer to answering the biggest mysteries of the cosmos, revealing the story of creation written in the light of the stars. The search for population 2 stars and their role in galactic evolution is far from over. In fact, with each new discovery, we are forced to refine our understanding of how the universe transformed from its early chaotic state into the structured cosmos we see today. These ancient stars are more than just remnants of the past. They are cosmic storytellers, carrying within them the secrets of a time before the familiar galaxies, planets, and stars we now know had even formed. One of the most fascinating aspects of studying population 2 stars is the ability to use them as markers of galactic assembly. The Milky Way did not form in isolation, it grew by absorbing smaller galaxies and merging with other star systems. This means that many of the population 2 stars we see today might not have originated in the Milky Way at all but instead were born in other, now defunct galaxies that were later cannibalized by our own. This leads us to the concept of stellar archaeology. Just as archaeologists dig through layers of sediment to uncover the history of ancient civilizations, astronomers sift through the chemical signatures and orbital motions of old stars to reconstruct the history of our galaxy. By identifying groups of population 2 stars with similar compositions and trajectories, scientists can trace them back to their original parent galaxies, revealing the long and complex process by which the Milky Way grew over billions of years. One particularly compelling example of this is the discovery of the Gaia-Enceladus merger. This was a massive collision between the Milky Way and a smaller galaxy billions of years ago, an event that left behind a population of stars with distinct chemical and orbital properties. Many of these stars are metal-poor, placing them firmly within the category of population 2 stars. The fact that they move in highly elliptical orbits compared to the rest of the Milky Way's stellar population suggests that they were not originally part of our galaxy but were instead captured through this ancient merger. This event was not unique. Over the course of cosmic history, our galaxy has merged with and absorbed many smaller star systems. Each time this happened, new populations of population 2 stars were introduced into the Milky Way, mixing with the existing stellar population and enriching the galaxy's chemical complexity. These mergers contributed to the overall metal enrichment of the interstellar medium, laying the groundwork for the formation of population 1 stars, including our Sun. But this process raises an interesting question. If population 2 stars were critical in enriching the galaxy with heavier elements, were there ever stars that formed in complete isolation, stars that never experienced enrichment from supernovae explosions? The answer lies in the search for population 3 stars, the hypothetical first stars of the universe. Population 3 stars, if they ever existed, would have been composed purely of hydrogen and helium, with no heavy elements at all. These stars would have been vastly different from anything we see today, likely more massive, hotter, and shorter-lived than later generations of stars. Because they burned through their fuel quickly and exploded in massive supernovae, they would have left behind no direct descendants. However, the elements they produced seeded the next generation of stars, population II stars. This means that when we study population II stars, we are indirectly studying the effects of population III stars. The chemical composition of population II stars provides clues about the kinds of elements that were available in the early universe, giving us a glimpse into how the first heavy elements were formed and distributed across space. One of the biggest challenges in modern astronomy is identifying the most metal per population II stars. These stars, which contain only trace amounts of elements heavier than hydrogen and helium, are thought to be the closest living relatives of population III stars. By analyzing their chemical fingerprints, astronomers can infer the properties of the first supernovae and how they shaped the development of the universe. A prime example is the discovery of the star SMSS J031300.36-670839.3, one of the most metal-poor stars ever found. This star contains almost no iron, suggesting that it formed from the remnants of an extremely early supernova, one that may have belonged to a population III star. By studying stars like this, astronomers can piece together the chain of events that led from the birth of the first stars to the formation of galaxies like the Milky Way. The search for metal-poor stars is not limited to the Milky Way. Other galaxies, particularly small dwarf galaxies orbiting the Milky Way, are also rich hunting grounds for ancient stars. Because these galaxies are less massive and have undergone fewer interactions with other systems, they often preserve some of the oldest stellar populations in the universe. Studying these stars helps astronomers understand how the earliest galaxies formed and evolved before being absorbed into larger structures. And yet, despite all we have learned, there are still profound mysteries surrounding population II stars. For instance, while we know that these stars played a crucial role in enriching the universe with heavy elements, we still do not fully understand the exact mechanisms that determined how these elements were distributed. Did supernovae explosions distribute these elements evenly, or were there pockets of the universe that remained metal-poor for longer periods? Additionally, there is the question of how many population II stars still exist today. Because these stars formed early in the universe's history, many of them have already reached the end of their lifetimes. However, the lowest mass population II stars could still be burning, as stars with lower masses tend to live much longer than their massive counterparts. These stars, often found in the galactic halo and globular clusters, provide a rare opportunity to study the conditions of the early universe in real time. Speaking of globular clusters, these dense collections of stars are among the oldest structures in the universe. Many globular clusters contain a significant population of metal-poor stars, making them invaluable laboratories for studying the early chemical evolution of galaxies. Because the stars in a globular cluster formed at roughly the same time, they offer a snapshot of a specific period in cosmic history, allowing astronomers to test theories about star formation and element production in the early universe. Ultimately, the study of population II stars is about much more than just individual stars. It is about understanding the grand narrative of the universe. These stars bridge the gap between the first moments after the Big Bang and the galaxies we see today. They reveal how the building blocks of planets, life, and everything we know came into existence. They are the missing pieces of the puzzle that connects the earliest cosmic structures to the modern universe. As telescopes become more advanced and our ability to analyze faint, distant light improves, we will continue to push the boundaries of our knowledge. The James Webb Space Telescope, for example, has already begun identifying some of the most distant and ancient galaxies ever observed. In the coming years, even more powerful telescopes, such as the Extremely Large Telescope, ELT, and the Nancy Grace Roman Space Telescope, will further refine our understanding of stellar evolution and the role of population II stars. The story of the universe is written in the light of its stars. And as long as there are unanswered questions about how the cosmos evolved, the search for these ancient celestial relics will continue. The mysteries of population 2 stars are far from being fully unraveled, and every new discovery brings us closer to understanding the fundamental processes that shape the universe itself. But for now, the biggest mystery remains: what other secrets are hidden within the oldest stars of the universe, waiting to be uncovered? The search for answers continues, driven by a single, profound question: how much of the universe's history is still locked away in the faint light of its oldest stars? Population 2 stars, the second generation of stars to form after the Big Bang, are more than just ancient remnants. They are cosmic fossils, holding within them the secrets of an era when the universe was still young and evolving. But even with all our advancements, there are still major gaps in our understanding. For instance, one of the biggest mysteries surrounding population 2 stars is exactly how and where they formed. While we know they emerged after the first stars, population 3 stars enriched the universe with heavy elements. The details of this transition remain unclear. What conditions led to the formation of the first population 2 stars? Were they formed in isolated pockets of space, or did they emerge in massive star-forming regions that later became the first galaxies? To answer these questions, scientists look at the chemical signatures of these ancient stars. The presence of elements like carbon, oxygen, and iron in population 2 stars tells us that they were born in regions already influenced by earlier supernovae. But not all population 2 stars have the same chemical composition. Some have extremely low metallicity, suggesting that they formed shortly after the first stars exploded, while others have slightly higher metal content, indicating that they were born after multiple cycles of star formation and supernova explosions. This variation in metal content is key to understanding how the first galaxies formed. If population 2 stars with different metal levels formed in different locations, this could mean that star formation was happening in isolated pockets throughout the early universe. On the other hand, if these stars show similar chemical patterns across large distances, this could suggest that the early universe was already well mixed with heavy elements from population 3 stars. One way to study this is through the detailed analysis of stellar atmospheres. The outer layers of a star act like a time capsule, preserving the chemical conditions of the gas cloud from which the star originally formed. By using high-resolution spectroscopy, astronomers can break down the light from population 2 stars into its component wavelengths, revealing which elements are present. This allows scientists to reconstruct the conditions of the early universe with incredible precision. But there's another question that remains unanswered. How did population 2 stars influence the formation of galaxies? While we know that they played a role in enriching the interstellar medium with heavier elements, we still don't fully understand how they shaped the structure of the first galaxies. Did they form in small, dense clusters, or were they spread out over vast distances? Were early galaxies dominated by population 2 stars? Or were these stars just a small fraction of a much larger and more diverse population? One clue comes from studying the oldest parts of our own galaxy. The Milky Way's galactic halo, a vast, spherical region surrounding the main disk, is home to some of the most ancient stars known. Many of these stars are population 2 stars, suggesting that the halo may be a fossilized remnant of the Milky Way's earliest days. By mapping the distribution of these stars, scientists can gain insight into how the first structures in the galaxy formed and evolved over time. Another important piece of the puzzle is globular clusters. These tightly packed groups of stars are among the oldest structures in the universe, with some clusters containing stars that are over 13 billion years old. Because the stars in a globular cluster all formed at roughly the same time, they provide a unique snapshot of the conditions that existed when they were born. The fact that many globular clusters contain metal-poor stars suggests that they were among the first star-forming regions in the Milky Way. But if that's the case, why do some globular clusters have stars with higher metallicity? One possible explanation is that these clusters experience multiple waves of star formation, with later generations of stars forming from gas that had already been enriched by earlier supernovae. This could mean that some globular clusters played a role in the transition from population 2 to population 1 stars, acting as cosmic incubators where heavy elements were gradually built up over time. This leads us to one of the most intriguing questions in modern astrophysics: what happened to the very first stars? While we have indirect evidence of their existence through the chemical signatures they left behind, no population 3 stars have ever been observed directly. Some scientists believe that these stars were simply too massive and short-lived to survive to the present day, burning out and exploding long before any telescopes could capture their light. But there's another possibility. What if some population 3 stars are still out there, hidden among the countless stars of the universe? If such stars exist, they would be unlike anything we have ever seen before, containing no elements heavier than hydrogen and helium. Finding just one of these stars would revolutionize our understanding of the early universe, providing a direct window into the moment when the first light sources began to shine. This is why astronomers continue to search for the most metal-poor stars in the universe. Every new discovery brings us closer to the elusive boundary between population 3 and population 2 stars, helping us piece together the story of how the cosmos evolved. And with next-generation telescopes like the James Webb Space Telescope and the Extremely Large Telescope, we may finally have the technology needed to detect these ancient relics. The study of population 2 stars is not just about understanding the past, it's also about predicting the future. The same processes that shaped the early universe are still at work today, driving the formation of new stars and galaxies. By studying how early generations of stars enriched their surroundings, we can gain insight into how future galaxies will evolve, and how the universe itself may continue to change over billions of years. In many ways, the story of population 2 stars is the story of the universe itself. These stars represent a critical turning point in cosmic history, bridging the gap between the first chaotic moments after the Big Bang and the structured galaxies we see today. They tell us how the first heavy elements were created, how galaxies formed, and how the cosmos became a place capable of supporting planets, life, and everything we know. And yet, despite all we have learned, there are still countless mysteries waiting to be uncovered. What other secrets are hidden in the light of these ancient stars? How many more discoveries remain just beyond the limits of our telescopes? And what will we find when we finally push the boundaries of our understanding to their absolute limits? The answers to these questions lie in the distant reaches of the universe, waiting for us to uncover them. And as long as there are mysteries to solve, the search will continue. The search for answers doesn't just rely on observing the stars themselves. It also involves studying the structures that formed around them. One of the most intriguing aspects of population 2 stars is their connection to the formation of the first galaxies. These stars played a crucial role in shaping the early universe, but the specifics of how they influenced galactic evolution are still being uncovered. For one, astronomers believe that population 2 stars were instrumental in the formation of the Milky Way's oldest structures. Some of the earliest galaxies were likely small, irregular, and chaotic, made up of loosely bound groups of stars. Over time, these galaxies merged and collided, gradually forming larger, more complex structures. The Milky Way itself is thought to have gone through this process, absorbing smaller galaxies and incorporating their stars into its halo. This means that many of the population 2 stars we see today might not have originated in our galaxy at all. Instead, they could have been born in ancient dwarf galaxies that were later swallowed by the Milky Way. This is supported by the discovery of stellar streams, long, thin trails of stars that stretch across the sky, marking the remnants of smaller galaxies that were torn apart by the Milky Way's gravity. Many of the stars in these streams are metal-poor, suggesting that they belong to the population 2 category. But how did population 2 stars contribute to the formation of galactic disks and bulges? The Milky Way, like many large galaxies, has a central bulge, a densely packed region of stars at its core. Some researchers believe that population 2 stars played a key role in shaping this structure, either by forming directly in the early galactic center or by being pulled inward over time. One possibility is that early star clusters, rich in population 2 stars, gradually sank toward the galactic center due to gravitational interactions. As these clusters merged, they may have contributed to the buildup of the bulge, creating the dense, metal-poor core we see today. Alternatively, population 2 stars may have formed in the outer regions of the galaxy and migrated inward over billions of years. Another critical question is how population 2 stars influenced the formation of population 1 stars, the metal-rich stars that dominate galaxies today. By enriching the interstellar medium with heavy elements, population 2 stars set the stage for the birth of new generations of stars. This process likely played out over several billion years, with each successive generation of stars containing more metals than the last. But there's a mystery here. Why do some regions of the galaxy contain more metal-poor stars than others? If population 2 stars were responsible for seeding the universe with heavy elements, we would expect to see a relatively even distribution of metals across the Milky Way. Instead, astronomers have found that some parts of the galaxy, particularly in the halo and certain globular clusters, remain extremely metal-poor. One explanation is that metal enrichment was not uniform in the early universe. Instead, heavy elements may have been distributed in pockets, with some regions receiving more enrichment than others. This could have been influenced by the way early supernovae exploded, dispersing elements unevenly across space. Some areas may have been enriched rapidly, while others remained metal-poor for much longer. This raises another question: how did early supernovae shape the evolution of galaxies? The explosions of population 3 and population 2 stars played a critical role in dispersing heavy elements, but they also had another important effect. They influenced the formation of new stars. When a massive star explodes, it releases enormous amounts of energy, sending shockwaves through the surrounding gas. These shockwaves can compress gas clouds, triggering new waves of star formation. This process, known as supernova-driven star formation, may have been one of the key mechanisms that shaped the early universe. In regions where population 2 stars exploded in rapid succession, bursts of star formation may have occurred, leading to the formation of dense, star-rich regions. In other areas, however, supernovae may have dispersed gas too quickly for new stars to form, delaying star formation and leaving behind metal-poor regions. Understanding these patterns is crucial for piecing together the history of our galaxy. By mapping the distribution of metal-poor stars, astronomers can reconstruct how the Milky Way evolved over billions of years. This is why surveys of ancient stars are so important. Each new discovery adds another piece to the puzzle. One particularly exciting discovery in recent years has been the identification of ultra-metal-poor stars in the galactic halo. Some of these stars have iron levels thousands of times lower than those found in the Sun, indicating that they formed shortly after the first stars in the universe. Studying these stars allows scientists to probe conditions that existed more than 13 billion years ago, offering a glimpse into a time when galaxies were just beginning to take shape. But despite all we've learned, there are still major gaps in our knowledge. For example, we still don't know exactly how the transition from population 3 to population 2 stars occurred. Did the first population 2 stars form immediately after the first supernovae, or was there a long gap before they appeared? Were population 2 stars more massive on average than later stars, or did they follow similar mass distributions? There's also the question of dark matter. While we can study the visible stars in the universe, most of the mass in galaxies is made up of something we can't see, dark matter. Scientists believe that dark matter played a crucial role in the formation of galaxies, providing the gravitational scaffolding that allowed gas clouds to collapse and form stars. But how did dark matter interact with population 2 stars? Did it influence their formation and distribution? And could studying these ancient stars help us learn more about the nature of dark matter itself? New technologies are helping to answer these questions. The James Webb Space Telescope, for example, is capable of detecting some of the most distant galaxies in the universe, allowing astronomers to study the light from stars that formed over 13 billion years ago. By analyzing this light, scientists can determine the composition of early stars and compare them to modern population 2 stars in our galaxy. If we find that distant, ancient stars share the same characteristics as those in the Milky Way's halo, it could confirm that our galaxy's oldest stars originated in the very first galactic structures to form in the universe. Another exciting tool is spectroscopic analysis, which allows astronomers to break down the light from stars into its component wavelengths. This technique is crucial for studying population 2 stars because it reveals their chemical composition. By analyzing the spectral lines of metal-poor stars, scientists can determine which elements were present in their birth environments, offering clues about the types of supernovae that preceded them. one of the biggest challenges in studying population 2 stars is finding them. Because they are so old, many have already exhausted their fuel and faded away. Others have been absorbed into the dense regions of galaxies, making them difficult to observe. However, some of the best places to look for them are in globular clusters, dense collections of stars that orbit the Milky Way and other galaxies. Globular clusters are thought to be among the oldest surviving structures in the universe, with some estimated to be over 13 billion years old. Many of the stars in these clusters are classified as population 2, meaning they formed during the early days of the galaxy. Because these clusters have remained relatively undisturbed for billions of years, they serve as cosmic time capsules, preserving the conditions of the ancient universe. But even within globular clusters, mysteries remain. For example, some clusters contain stars with different levels of metal enrichment, suggesting that multiple generations of stars may have formed within them. This challenges the traditional view that globular clusters formed in a single burst of star formation. Instead, it suggests that some clusters may have had more complex histories, with new stars forming from gas enriched by earlier generations. This idea ties into a larger question about how galaxies evolve over time. If some globular clusters experience multiple waves of star formation, it could mean that early galaxies followed a similar pattern, with bursts of star formation triggered by mergers, supernovae, and other cosmic events. This could help explain why some regions of the Milky Way are more metal-rich than others and why certain structures, like the thick disk and the halo, contain stars with very different compositions. Another key area of research is the role of population 2 stars in the reionization of the universe. Reionization was a period in cosmic history when the first stars and galaxies ionized the neutral hydrogen that filled the universe, allowing light to travel freely for the first time. While population 3 stars are often credited with kickstarting this process, population 2 stars likely played a major role in sustaining it. Because population 2 stars formed in large numbers, they would have contributed significant amounts of ultraviolet radiation, which helped keep the universe ionized. This means that the transition from the cosmic dark ages to the transparent universe we see today was not a sudden event but a gradual process influenced by multiple generations of stars. By studying the oldest population 2 stars, scientists can gain a better understanding of how this transition unfolded and how it shaped the evolution of galaxies. But the mysteries don't end there. Some population 2 stars exhibit unusual chemical signatures that don't fit neatly into existing models. For example, some stars have been found with unexpectedly high levels of certain elements, such as carbon and nitrogen. These anomalies suggest that the processes that governed early star formation were more complex than we previously thought. One possibility is that some early stars underwent unusual nuclear reactions, producing elements in different proportions than later generations. Another possibility is that early supernovae ejected their elements in ways that varied depending on the mass and rotation of the exploding star. By studying these anomalies, astronomers hope to refine their models of stellar evolution and gain new insights into the first few billion years of cosmic history. Recent discoveries have also raised questions about the lifespans of population 2 stars. Traditional models suggest that the most massive population 2 stars would have burned through their fuel quickly and exploded as supernovae, while lower mass stars could have survived to the present day. However, some ancient stars appear to be more massive than expected, leading scientists to wonder whether some population 2 stars lived longer than predicted or whether they formed in different environments than previously thought. There's also the question of what happens to population 2 stars as they reach the end of their lifespans. While some explode as supernovae, others evolve into white dwarfs, dense, Earth-sized remnants that slowly cool over billions of years. In some cases, these white dwarfs can merge, producing powerful bursts of energy that may have contributed to the reionization of the universe. Understanding the life cycles of population 2 stars is not just a matter of studying the past. It also has implications for the future. As we continue to search for habitable exoplanets, the composition of their parent stars becomes an important factor. Stars that formed in metal-poor environments may have very different planetary systems than those formed in metal-rich environments, influencing the potential for life elsewhere in the universe. This brings us to one of the most intriguing questions of all. Could population 2 stars have hosted planets capable of supporting life? Traditionally, astronomers assumed that metal-poor stars were unlikely to have planets because heavy elements are necessary for planet formation. However, recent discoveries have challenged this view. Some metal-poor stars have been found with planetary systems, suggesting that planets may have formed earlier in the universe than we once thought. If this is true, it opens up the possibility that life could have emerged much earlier than expected. While the early universe was a harsh and chaotic place, with frequent supernovae and intense radiation, it's possible that some planetary systems found safe havens where life could take root. If life did emerge around population 2 stars, it would mean that the search for extraterrestrial life should extend to some of the oldest stars in the galaxy. Population 2 stars are more than just relics of the past. They are living records of the universe's history. Each one carries the fingerprints of the cosmic events that shaped it, from the explosions of population 3 stars to the merging of galaxies and the evolution of the Milky Way. By studying these stars, we are not just looking back in time, we are uncovering the story of how the universe came to be and how it continues to evolve. And perhaps, somewhere among these ancient stars, we may find answers to some of the greatest mysteries of all. The discoveries regarding population 2 stars have already reshaped our understanding of galactic evolution, but they also lead us to question the processes at work during the earliest stages of the universe. The first stars that formed, often referred to as population 3 stars, were composed almost entirely of hydrogen and helium, the simplest elements, formed shortly after the Big Bang. As these stars evolved and died, they released heavier elements into space, creating the chemical building blocks for subsequent generations of stars, including the population 2 stars. The journey of elements through stellar generations is a continuous cycle that connects the past to the present. Each time a star dies, it leaves behind remnants that enrich the surrounding gas clouds, fostering the birth of new stars. Population 2 stars played a crucial role in this process. They served as the first true, metal-rich stars, containing not just hydrogen and helium, but also traces of elements such as carbon, oxygen, and iron, elements that are essential for the formation of planets, and possibly even life itself. Yet, one of the key mysteries is just how the population 2 stars came to form. After the first stars, which were predominantly composed of hydrogen and helium, died in violent supernova explosions, they released the heavier elements that had been synthesized in their cores. These materials mixed with surrounding hydrogen and helium, eventually leading to the formation of the next generation of stars. However, the exact process by which these new stars formed is still a subject of ongoing research. One prevailing theory is that the metal-enriched gas clouds from population 3 supernovae were the building blocks for population 2 stars. These clouds were likely cooler and denser than those that gave rise to the first generation, leading to the formation of stars with greater chemical diversity. The gas clouds would have collapsed under their own gravity, igniting nuclear fusion at their cores and producing stars with a wide range of characteristics. Some of these stars were massive and short-lived, while others were smaller and longer-lived, contributing in different ways to the chemical enrichment of the galaxy. The fact that population 2 stars have lower amounts of heavy elements than modern stars has important implications for how galaxies evolve. For example, metal-poor stars are thought to be less efficient at forming planets because heavy elements are key to the process of planetary formation. This raises the question of whether early galaxies were capable of sustaining life, and if so, what conditions would have been necessary for planets to form and life to emerge. Population 2 stars also provide crucial clues about the earliest stages of the Milky Way galaxy's formation. The stars found in the Milky Way's halo and thick disk, which are composed primarily of population 2 stars, are thought to be remnants of the galaxy's ancient formation. These stars are often found in isolated regions, suggesting that they originated in the early, chaotic periods of galactic formation, before the galaxy's structure was fully settled. The study of population 2 stars offers valuable insights into the nature of galaxy formation itself. According to the current models, the Milky Way was formed through a series of mergers with smaller galaxies in the early universe. Each of these mergers could have triggered bursts of star formation, enriching the galaxy with new stars, gas, and metals. As these stars age and die, they contribute to the ongoing process of galactic evolution, shaping the structure and composition of the Milky Way and other galaxies. In recent years, scientists have developed new techniques to study population II stars more effectively. By using advanced telescopes and spectrographs, they can now analyze the light from distant stars in greater detail, allowing for more precise measurements of their chemical composition, age, and motion. These tools provide a clearer picture of how stars formed and evolved in the early universe, helping to answer some of the most fundamental questions about the origins of the cosmos. One of the most significant advancements in this field has been the study of the oldest known stars in the Milky Way. These ancient stars are thought to be more than 13 billion years old, making them some of the oldest objects we can observe. By studying these stars, astronomers can trace the history of the universe back to its earliest stages. These stars also provide insights into the processes that led to the formation of the first galaxies, which were crucial for the reionization of the universe, a process that allowed light to travel freely across the cosmos for the first time. The discovery of near-pristine population II stars is another exciting development. These stars have very low levels of metal content, indicating that they were formed before the first significant supernovae occurred. They are relics of the earliest stages of the universe and serve as time capsules that can help us understand the conditions that existed in the primordial universe. By analyzing their chemical makeup, scientists hope to learn more about the first stars and the nature of the materials that were available for star formation in the early universe. While the study of population II stars has already led to groundbreaking discoveries, many questions remain unanswered. For example, how exactly did the first galaxies form, and what role did population II stars play in this process? How did the intergalactic medium evolve to allow the formation of the first stars, and what were the specific conditions that triggered this process? Furthermore, what can population II stars tell us about the future of the Milky Way and other galaxies? By continuing to explore these questions, we can gain a deeper understanding of the history and evolution of the universe. In the grand scheme of cosmic evolution, population II stars represent a crucial turning point. They were the first stars to form after the first generation of stars, and they played a central role in enriching the universe with the elements necessary for life. Their study not only provides insights into the past but also offers a glimpse into the future of galactic evolution, helping us understand how galaxies like the Milky Way formed and how they will continue to evolve in the coming billions of years. As we continue to explore the universe, we will undoubtedly uncover more secrets about these ancient stars and their role in shaping the cosmos. With every new discovery, we are one step closer to answering some of the most profound questions about the nature of the universe and our place within it. The study of population II stars is just one chapter in the ongoing story of cosmic evolution, and as technology advances and our understanding deepens, we will continue to unlock the mysteries of the stars that formed after the first generation, revealing more about the origins of galaxies, stars, and planets, and perhaps even life itself. As we continue to delve into the mysteries of population II stars, their role in the broader context of cosmic history becomes ever clearer. These stars were instrumental in the early stages of galactic evolution, acting as bridges between the primordial universe, filled with only hydrogen and helium, and the more complex, metal-rich universe that we observe today. By shedding light on these early stars, we begin to piece together the puzzle of how galaxies, stars, and even life itself came to exist in the way we know it. To fully appreciate the role of population II stars, it is essential to understand the relationship between these stars and the interstellar medium, the gas and dust that fill the space between stars. The heavy elements produced by population II stars, such as carbon, oxygen, and iron, were spread throughout the galaxy during their lifetimes and explosive deaths, enriching the interstellar medium. This enriched material then became the building blocks for new generations of stars, planets, and other celestial objects. The heavy elements allowed for the formation of complex molecules, which may have been necessary for the emergence of life. The process of stellar nucleosynthesis, by which stars produce elements through fusion reactions in their cores, is central to this story. In the cores of population II stars, hydrogen and helium fuse together to create heavier elements. Over the course of their lives, these stars produced an array of elements, from carbon to iron, which were then released into the surrounding space when the stars reached the end of their life cycles. These elements, in turn, enriched the gas clouds from which the next generation of stars would form. The cycle of stellar birth, evolution, and death continues, with each generation of stars building upon the foundation laid by the previous ones. One of the most intriguing aspects of population II stars is their role in the early stages of galaxy formation. The Milky Way, like many galaxies, is thought to have formed through a process of hierarchical merging, in which smaller galaxies collided and merged to create the galaxy we see today. Population II stars are believed to have formed in these early, small protogalaxies, before the larger, more complex structure of the Milky Way emerged. As these early stars formed and died, they contributed to the formation of the Milky Way's halo, a vast, diffuse region of stars and gas that surrounds the galaxy's disk. The halo is thought to be a relic of the early stages of galaxy formation and contains a large number of population II stars. The stars in the Milky Way's halo are often referred to as old stars, because they are believed to have formed more than 10 billion years ago. These stars provide a snapshot of the galaxy's early history, offering clues about the conditions that existed during the formation of the first galaxies. The stars in the halo are also important for understanding the dynamics of galactic evolution, as they help to reveal the processes that shape the Milky Way's structure. In addition to their role in the formation of the Milky Way, population II stars also provide insights into the broader process of galactic evolution. Observations of other galaxies have shown that galaxies are not static entities, but rather, they evolve over time through a series of complex processes. One of the key factors in this evolution is the interplay between stars, gas, and dark matter. The study of population II stars offers important clues about how these processes work, and how galaxies like the Milky Way grew and evolved from their humble beginnings. The discovery of population II stars in other galaxies has been an important step in understanding the broader picture of galactic evolution. By studying the chemical composition, age, and distribution of these stars and galaxies outside the Milky Way, astronomers can gain valuable insights into the history and evolution of other galaxies. The discovery of metal-poor stars in the halos of distant galaxies, for example, suggests that these galaxies also underwent similar processes of stellar evolution and chemical enrichment, helping to reinforce the idea that population II stars were a key component of early galactic formation. In recent years, advancements in observational technology have allowed astronomers to study population II stars in greater detail than ever before. The advent of powerful telescopes, such as the Hubble Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, has enabled scientists to observe distant stars and galaxies with unprecedented precision. By studying the light from these stars, astronomers can measure their chemical composition, age, and motion, providing a detailed picture of how these stars formed and evolved. The study of population II stars is also advancing through the use of computer simulations. By modeling the formation and evolution of stars and galaxies, scientists can test different hypotheses about how galaxies grew and developed over time. These simulations allow astronomers to explore a wide range of scenarios, helping to refine our understanding of the processes that govern galactic evolution. For example, simulations of early galaxy formation have shown that the interplay between gas, stars, and dark matter played a crucial role in determining the structure and composition of galaxies like the Milky Way. As our understanding of population II stars continues to evolve, we are uncovering new insights into the early universe and the processes that shaped the galaxies we observe today. These stars are not only important for understanding the history of the Milky Way but also for exploring the broader questions of how galaxies, stars, and planets formed. The study of these ancient stars provides a glimpse into the past, offering valuable clues about the conditions that existed in the early universe and the forces that shaped the cosmos. Population II stars are also important for understanding the formation of planets and the potential for life in the universe. The heavy elements produced by these stars, such as carbon and oxygen, are essential for the formation of planets and, ultimately, life as we know it. By studying these stars, we gain a deeper appreciation for the complex processes that lead to the creation of planets and the conditions that may be necessary for life to emerge. The role of population 2 stars in galactic evolution is not just a historical curiosity, but a crucial part of the ongoing story of the universe. As we continue to explore the cosmos, we will undoubtedly uncover more secrets about these ancient stars and their role in shaping the universe. With each new discovery, we come closer to understanding the origins of galaxies, stars, and planets, and perhaps, one day, even life itself. Population 2 stars are central to our understanding of galactic evolution. They represent a crucial stage in the ongoing cycle of star formation, evolution, and death. These stars not only provide insight into the early stages of galaxy formation but also play a key role in enriching the universe with the heavy elements necessary for the creation of planets and life. By continuing to study these ancient stars, we are uncovering new insights into the history of the cosmos, helping to answer some of the most profound questions about the nature of the universe and our place within it. The significance of population 2 stars doesn't just lie in their role in galactic evolution, but also in their contribution to the fabric of the universe itself. As one of the earliest generations of stars, they were fundamental in shaping not only the galaxies we see today but also the very chemistry of the universe. These stars are often referred to as metal-poor, because they contain very little of the heavier elements that make up most of the objects we encounter in our daily lives. They are instead primarily composed of hydrogen and helium, the simplest elements that were formed in the Big Bang. Despite their metal-poor composition, population 2 stars were crucial in seeding the universe with the elements necessary for more complex structures. When these stars reached the end of their lifespans, they underwent supernova explosions that released these light elements and enriched the surrounding gas with heavier elements. This process, called stellar nucleosynthesis, created an interstellar medium that was richer in metals than before. This metal-rich gas would eventually collapse under gravity to form new generations of stars, many of which contained higher concentrations of heavier elements. The heavy elements that were synthesized in population 2 stars, elements like carbon, oxygen, iron, and nitrogen, are the building blocks of life as we know it. It's impossible to overstate how crucial these elements are for the development of planets, complex molecules, and biological processes. Without these elements, the chemistry of life would be drastically different. Through their deaths, population 2 stars played a key role in the evolution of chemistry in the universe. A profound mystery arises when we consider how these first stars were born in the first place. The very formation of population 2 stars depends on the conditions that existed in the early universe, shortly after the Big Bang. The universe was initially composed almost entirely of hydrogen and helium, and as the first stars formed, they began to fuse these elements into heavier ones. The process of creating stars in such an environment is not fully understood, as the early universe was devoid of the heavier elements that today play a crucial role in star formation. Yet somehow, these early stars were able to condense and ignite, starting the process of stellar evolution that would ultimately lead to the formation of galaxies. The precise mechanism by which the first stars, referred to as population 3 stars, formed remains an open question in astrophysics. These stars are believed to have been much larger and more massive than the stars we see today. Their formation may have been aided by the absence of metals, allowing hydrogen and helium to collapse under gravity and form massive, hot stars. The intense heat and pressure in the cores of these stars triggered nuclear fusion, which in turn allowed these stars to produce heavier elements. When these population 3 stars died, their supernova explosions released an unprecedented amount of energy and heavy elements into space, which seeded the interstellar medium with the raw materials needed to form the next generation of stars, population 2 stars. These stars were therefore the progeny of the first stellar generation, inheriting their chemical composition and continuing the cycle of galactic enrichment. The stars that followed in their footsteps, population 2 stars, were not only a byproduct of this process but played a more active role in the evolution of the universe. As they aged and died, their supernovae enriched the gas surrounding them, creating an environment that was conducive to the formation of new stars. Over time, these new generations of stars continued to evolve, each one contributing to the growing complexity of the universe. These stars paved the way for even more advanced stages of stellar evolution and laid the groundwork for the formation of galaxies like the Milky Way. As time passed, population 2 stars continued to be a critical component of the Milky Way's halo. The stars in the halo of the Milky Way are a relic of an earlier time in the galaxy's history, providing a glimpse into the processes that led to the formation of the galaxy. The Milky Way's halo is thought to be made up of stars that formed from gas that had been enriched by the first generations of stars, including population 2 stars. These stars are often much older than the stars in the galaxy's disk and represent the early stages of galactic evolution. While the Milky Way's disk, which contains the Sun and most of the galaxy's stars, is made up of younger, metal-rich stars, the halo is populated by older, metal-poor stars. These stars were formed in the early stages of the galaxy's history, and their study can provide valuable insights into the processes that govern the formation of the Milky Way. Understanding how these stars formed and evolved is key to understanding the larger processes of galactic formation and evolution. The discovery of population 2 stars in other galaxies has further enhanced our understanding of galactic evolution. By studying the stars in the halos of distant galaxies, astronomers can gain insights into the history of these galaxies and the processes that led to their formation. The presence of population 2 stars in distant galaxies suggests that many galaxies, like the Milky Way, underwent similar processes of stellar evolution and chemical enrichment. This helps to reinforce the idea that the cycle of star formation, evolution, and death is universal throughout the cosmos. The role of population 2 stars in galactic evolution is not just about their contribution to the creation of new stars, but also about their impact on the dynamics of galaxies themselves. Population 2 stars are often found in the halos of galaxies, far from the central regions where most of the galaxy's stars are concentrated. These stars are thought to have formed in the early stages of galactic formation, when the galaxies were much smaller and less structured. As these galaxies grew through mergers and accretion of gas and stars, the population 2 stars were scattered across the galaxy, creating the vast halos that we observe today. These halos are a key feature of many galaxies, including the Milky Way. The stars in the halo play an important role in the overall structure and dynamics of the galaxy. They are often thought to be remnants of the early stages of galactic formation, providing a record of the conditions that existed when the galaxy first formed. The study of these stars can provide important clues about the processes that shaped galaxies and the role of dark matter, gas, and other factors in the evolution of galactic structures. As we continue to study population 2 stars, new technologies and advancements in observational techniques promise to provide even more detailed insights into the role of these stars in galactic evolution. With the advent of next-generation telescopes and observatories, we will be able to study these ancient stars in unprecedented detail, unlocking more of the mysteries of the universe's early history. From the formation of galaxies to the creation of the elements essential for life, population 2 stars remain an essential piece of the cosmic puzzle. Their study continues to yield valuable information about the origins and evolution of the universe, and as our understanding of these stars deepens, so too does our understanding of the cosmos itself. In the future, as we push the boundaries of our understanding, it's likely that we will uncover even more about these ancient stars and their role in shaping the universe. Whether it's through direct observations of distant population 2 stars or through simulations that model the complex processes of galactic evolution, we are only scratching the surface of what these stars can teach us. The story of population 2 stars is far from over, and each new discovery brings us one step closer to understanding the forces that shape the universe and the role these stars played in the grand cosmic narrative. The role of population 2 stars in galactic evolution is integral to our understanding of how galaxies, stars, and elements formed. These stars not only enriched the universe with the building blocks necessary for life, but they also played a pivotal role in the development of galaxies like the Milky Way. From their formation in the early stages of cosmic history to their explosive deaths that seeded the universe with heavy elements, population 2 stars were a driving force in the evolution of the cosmos. As we continue to study these ancient stars, we gain valuable insights into the processes that shape the universe, bringing us closer to understanding our place in the vast, complex expanse of space. As we dive deeper into the study of population II stars, we begin to uncover their profound impact on the formation of galaxies, including the Milky Way. The stars that make up the stellar halos of galaxies, like population II stars, offer a unique glimpse into the early universe, allowing astronomers to piece together the history of galactic formation and the processes that led to the galaxies we see today. These ancient stars carry with them the secrets of the early universe, giving us a window into the conditions that existed billions of years ago. Population II stars are critical to understanding how galaxies like the Milky Way were constructed. These stars were born from gas clouds that had been enriched by the explosive deaths of earlier generations of stars, including population III stars. The gas that formed population II stars was significantly more metal-rich than the gas that formed the first stars, allowing these new stars to form with higher levels of heavy elements. This was a crucial step in the process of galactic evolution, as the presence of metals allowed for the formation of planets, the building blocks of life, and other complex structures within galaxies. As population II stars aged and died, they continued to enrich the interstellar medium with heavier elements. Their explosive deaths and supernovae created an environment that was increasingly rich in metals, allowing for the formation of new generations of stars that were progressively more metal-rich. This process, known as stellar nucleosynthesis, continues to be a driving force in the evolution of galaxies. Each new generation of stars, born from gas that has been enriched by the death of earlier stars, brings with it the potential for more complex structures, including planets, which are essential for life. The formation of these new generations of stars was not limited to the inner regions of galaxies, but also took place in the outskirts, where population II stars are often found. These stars are a remnant of the early stages of galactic formation, providing insight into the conditions that existed when galaxies were first forming. By studying the population II stars and the halos of galaxies, astronomers can trace the history of star formation and understand how the dynamics of galaxies have evolved over time. One of the most important discoveries in the study of population II stars has been their role in understanding the age and history of galaxies. Because these stars are among the oldest in the universe, their age can be used to estimate the age of the galaxies they reside in. By determining the ages of population II stars, astronomers can determine when galaxies like the Milky Way first began to form. This, in turn, gives us a better understanding of the timeline of cosmic evolution, helping to refine our models of galaxy formation and the processes that shaped the early universe. The study of population II stars has also revealed important clues about the role of dark matter in galactic evolution. Dark matter is thought to make up a significant portion of the mass in galaxies, yet it is invisible and can only be detected through its gravitational effects. The distribution of population II stars in the halos of galaxies provides important insights into the distribution of dark matter. The gravitational influence of dark matter is thought to be responsible for the existence of these stellar halos, and the way in which these stars are spread out across the galaxy's outskirts provides clues about the distribution and behavior of dark matter. In addition to their role in galactic evolution, population II stars also provide valuable information about the formation of the elements that make up our universe. These stars were responsible for synthesizing many of the elements that are essential for life, including carbon, oxygen, and iron. By studying the chemical composition of population II stars, astronomers can gain a better understanding of how these elements were created and how they were distributed throughout the universe. This knowledge is crucial for understanding the origins of life and the processes that led to the formation of the Earth and other planets. The study of population II stars has also shed light on the complex processes of stellar evolution. These stars are typically much older than the stars in the disk of galaxies, and their study provides valuable information about the different stages of stellar life. Population II stars are often in the later stages of their evolution, having already undergone the fusion of hydrogen and helium and begun to fuse heavier elements. This makes them a valuable source of information about the life cycles of stars and the processes that lead to their death. As technology continues to advance, astronomers are able to study population II stars in greater detail than ever before. Next-generation telescopes, such as the James Webb Space Telescope, are designed to observe the faint light from distant stars, allowing scientists to study these ancient objects in unprecedented detail. With these tools, we can probe deeper into the universe's history and continue to unravel the mysteries surrounding these ancient stars and their role in shaping the cosmos. In addition to their direct contribution to the evolution of galaxies and the formation of heavy elements, population 2 stars have another fascinating role in the ongoing development of the universe. Their presence is a testament to the gradual buildup of complexity in the cosmos. While the first stars, population 3 stars, were likely composed of only hydrogen and helium, the existence of population 2 stars indicates a gradual enrichment of the universe, as these stars help produce the elements that are necessary for the formation of planets and life. Each generation of stars, starting from the first to the last, has contributed to the increasing complexity of the universe. The relationship between population 2 stars and the galaxies in which they reside is also a source of significant interest. The study of these stars offers insights not just into the processes that govern stellar life but also into the intricate dynamics of galaxies. Population 2 stars are often found in the outer regions of galaxies, and their study allows astronomers to examine the evolution of the galaxy's structure. Understanding the distribution and characteristics of these stars can help to reveal how galaxies formed, how they grew, and how they continue to evolve over time. The relationship between the stellar population of a galaxy and its chemical evolution is a key area of research in modern astrophysics. As population 2 stars continue to age and die, they release important clues about the processes that shape the galaxy and the universe as a whole. Through their study, we are able to learn more about the history of the cosmos and the forces that led to the formation of stars, planets, and galaxies. The role of population 2 stars in galactic evolution is of profound significance. These stars played a central role in the formation of galaxies, the creation of the elements necessary for life, and the enrichment of the universe with metals. Through their study, we gain invaluable insights into the early universe, the processes that shaped galaxies, and the forces that led to the formation of the complex and diverse cosmos we observe today. Population 2 stars not only provide a glimpse into the distant past but also hold the key to understanding the future evolution of the universe. As our technology continues to advance, we can expect even greater discoveries that will deepen our understanding of these ancient stars and their role in the grand cosmic story. As we continue our journey through the universe and delve further into the role of population 2 stars, it's essential to explore how they've not only contributed to the composition of the universe but have also acted as cosmic time capsules, preserving vital information about the conditions and processes of the early universe. These stars are like relics, carrying within them the imprint of a time long gone. By studying them, we can unlock mysteries that span the entirety of cosmic history, helping us understand how the universe has evolved from a young, simple state to the complex and dynamic system we observe today. One of the most fascinating aspects of population 2 stars is their ability to reveal insights into the first stages of galaxy formation. These stars were formed from the same primordial gas that would eventually give birth to galaxies. The process of star formation within these early gas clouds was significantly different from what we observe today. These ancient clouds were made primarily of hydrogen and helium, with only trace amounts of heavier elements. The stars that formed from these clouds, known as population 3 stars, are believed to have been massive and short-lived, burning through their fuel quickly and ending their lives in catastrophic supernovae that released heavy elements into the surrounding gas. The remnants of these explosions then seeded the formation of population 2 stars, which were born in gas clouds enriched by these heavy elements. The study of population 2 stars provides a unique window into this early phase of galactic evolution. Unlike younger stars, which are typically surrounded by dust and gas that obscure our view, population 2 stars are found in the halos of galaxies, far from the galactic center. These regions are less affected by the ongoing processes of star formation, making it easier for astronomers to observe and analyze the properties of these ancient stars. By studying their chemical composition and age, scientists can determine how the heavy elements created in earlier supernovae were distributed throughout the universe and how they contributed to the formation of later generations of stars, planets, and galaxies. Population 2 stars also offer insight into the chemical evolution of galaxies. As these stars age and eventually die, they release their outer layers into the interstellar medium, enriching the surrounding gas with heavier elements. This process, known as stellar winds, contributes to the gradual buildup of metals in the galaxy, providing the raw materials for future generations of stars and planets. Over time, as more population 2 stars die and release their material, the interstellar medium becomes increasingly enriched with heavy elements, which in turn affects the properties of the stars and planets that form from it. This ongoing process of enrichment has been a key factor in the evolution of galaxies, enabling the formation of more complex structures and the potential for life as we know it. One of the most significant contributions of population 2 stars to galactic evolution is their role in the formation of the stellar halo, a vast region of stars that surrounds a galaxy's disk. The stars in the stellar halo are thought to be some of the oldest in the galaxy, and they provide crucial information about the early stages of galactic formation. These stars were likely part of the first generations to form in the galaxy, and were scattered throughout the halo during the galaxy's formation. Over time, the gravitational forces within the galaxy caused these stars to settle into their current positions, creating a distinct population of stars that are separate from those in the galactic disk. By studying the distribution and properties of these stars, astronomers can learn more about how galaxies form and evolve, and how the early phases of galactic history shaped the galaxies we observe today. Another important aspect of population 2 stars is their connection to the formation of globular clusters. These clusters are dense collections of stars that are typically found in the halos of galaxies. Many of these clusters are composed primarily of population 2 stars, and their study provides valuable insight into the early stages of star formation. Globular clusters are thought to be some of the oldest structures in the universe, and they contain some of the oldest stars ever observed. By studying these clusters, astronomers can gain a better understanding of the conditions that existed when the first stars and galaxies were forming, and how the early universe evolved over time. Population 2 stars are also important in the context of stellar evolution. These stars are typically older and less massive than the stars we observe in the galactic disk, and they are often in the later stages of their evolution. As they age, population 2 stars exhaust their nuclear fuel and undergo a variety of processes that alter their structure and composition. Some of these stars may become red giants, while others may undergo dramatic transformations such as becoming white dwarfs or exploding as supernovae. These processes are crucial for understanding how stars evolve over time, and how they contribute to the ongoing cycle of star birth and death within galaxies. In the context of galaxy formation, population 2 stars are also valuable for understanding the role of dark matter. Dark matter is thought to make up a significant portion of a galaxy's mass, yet it cannot be directly observed. Instead, its presence is inferred through its gravitational effects on visible matter, such as stars and gas. Population 2 stars, located in the outer regions of galaxies, provide valuable information about the distribution of dark matter in galaxies. By studying the motion and distribution of these stars, astronomers can infer the presence of dark matter and gain a better understanding of how it influences the formation and evolution of galaxies. Moreover, population 2 stars have been crucial in our understanding of the universe's age and the timeline of its evolution. By studying the ages of these stars, scientists can estimate when galaxies first began to form and when the first generations of stars were born. This, in turn, provides valuable information about the age of the universe itself. The oldest population 2 stars are thought to be around 13 billion years old, providing a benchmark for understanding the timescale of cosmic events. As more advanced telescopes and observational techniques become available, astronomers will continue to refine our understanding of the age of the universe and the processes that led to the formation of galaxies and stars. The study of population 2 stars has also revealed important information about the chemical composition of the universe. These stars, being among the oldest in the universe, provide a snapshot of the early chemical makeup of the cosmos. By analyzing the chemical composition of population 2 stars, astronomers can determine the abundance of elements such as carbon, oxygen, and iron, which are essential for the formation of planets and life. This knowledge is crucial for understanding the origins of life and the processes that led to the creation of the elements that make up the Earth and other planets. In addition, the study of population 2 stars helps to reveal the complex interactions between stars and the interstellar medium. These interactions are central to the processes of star formation, evolution, and death. As population 2 stars age, they influence the gas and dust around them, contributing to the ongoing cycle of star birth and death. This cycle, known as stellar feedback, plays a key role in shaping the structure and evolution of galaxies. By studying the effects of population 2 stars on their environment, astronomers can gain a deeper understanding of the forces that drive the evolution of galaxies and the universe as a whole. As our technology advances, the study of population 2 stars will continue to yield new insights into the mysteries of the universe. With the advent of more powerful telescopes and observational instruments, we can expect to uncover even more information about these ancient stars and their role in the evolution of galaxies and the universe. Through their study, we are gaining a deeper understanding of the processes that shape the cosmos, from the formation of the first stars to the birth of galaxies, planets, and life itself. The role of population 2 stars in galactic evolution is both profound and far-reaching. These stars have played a pivotal role in the formation of galaxies, the creation of the elements necessary for life, and the enrichment of the universe with metals. Their study provides valuable insights into the early stages of cosmic history and helps to illuminate the processes that have shaped the universe as we know it. As we continue to explore the mysteries of the cosmos, population 2 stars will remain a central focus of our investigations, offering a glimpse into the past and a deeper understanding of the forces that have shaped the universe over billions of years. The journey to uncover the secrets of these ancient stars is far from over, and with each new discovery, we move closer to unraveling the mysteries of the universe. Continuing our exploration of the fascinating role that population 2 stars have played in galactic evolution, it's important to address how these ancient stars connect to broader cosmic phenomena and to the cycles that have influenced the structure of galaxies. Population 2 stars are not merely isolated relics of the past, but active participants in the ongoing saga of the universe's growth and transformation. Their contributions can be traced across many levels of cosmic history, from the emergence of galaxies to the development of life-supporting conditions on planets. One of the most intriguing aspects of population 2 stars is their relationship with the formation of other stellar populations within galaxies. While population 2 stars themselves were born from gas clouds enriched by the first generation of supernovae, their presence and ongoing evolution helped set the stage for the birth of later generations of stars, including the younger population 1 stars. Population 1 stars are typically younger, richer in heavier elements, and more abundant in the inner regions of galaxies, particularly in the spiral arms. These stars evolved in the aftermath of the contributions made by population 2 stars, which enriched the interstellar medium with heavier elements. Without the chemical enrichment provided by population 2 stars, the formation of more complex stellar systems, including those capable of hosting planetary systems like our own, would not have been possible. The interplay between these stellar populations tells us something crucial about the ongoing process of galactic evolution. Galaxies evolve over time not just because of the accumulation of new stars but also because of the interactions between older stars and the interstellar medium. Population 2 stars acted as early stellar factories that pumped new elements into the surrounding gas, which in turn was recycled to form newer generations of stars. In a sense, population 2 stars can be viewed as the cosmic forerunners of the complex and varied stellar systems that we see today. Moreover, as we continue to observe and model the formation and evolution of galaxies, we find that population 2 stars offer essential clues about how galaxies grow. Many of the most ancient galaxies in the universe are thought to have formed from the collapse of early gas clouds that initially contained just hydrogen and helium. These gas clouds were later enriched with metals from the explosive deaths of population 3 stars, and the resulting gas then went on to form population 2 stars. Understanding how these stars and their progenitors interacted with their environment is a crucial part of understanding how the earliest galaxies evolved. One of the most important things to note about population 2 stars is their role in seeding the universe with elements crucial for life. These stars, as they aged, underwent processes that produced a variety of elements, from carbon to iron, through nuclear fusion in their cores. Upon reaching the end of their lives, these stars released their outer layers through powerful stellar winds or, in some cases, exploded as supernovae. These events enriched the surrounding interstellar medium with these newly created elements. As these heavy elements spread throughout the galaxy, they provided the building blocks for later star systems, including the formation of rocky planets and complex molecules. Without this enrichment, the complex chemistry required for life, as we know it, would have been impossible. While the heavy elements produced by population 2 stars were important for later star and planet formation, they also contributed to the broader interstellar medium, changing the environment in which future stars were born. The metals released by these stars altered the composition of the gas clouds from which new stars and planetary systems would form. These changes in composition influenced everything from the size and brightness of new stars to the chemical composition of planets. The eventual formation of the solar system, for example, was made possible by the elements created in these ancient stars. Another significant aspect of population 2 stars is their connection to the theory of stellar population gradients in galaxies. It is known that older, metal-poor stars are more likely to be found in the halos or outer regions of galaxies, while younger, metal-rich stars tend to be concentrated toward the center of galaxies. This gradient in metallicity, the abundance of elements heavier than hydrogen and helium, provides a valuable tool for astronomers seeking to understand the structure and formation history of galaxies. Population 2 stars, being old and metal-poor, form a key part of this gradient, offering astronomers clues about the conditions that existed in the early universe and how they shaped the galaxies we observe today. Population 2 stars also have significant implications for our understanding of the age of the universe. By studying the ages of these stars, scientists have been able to refine their estimates of when galaxies first began to form, and when the first generations of stars were born. The oldest known population 2 stars are believed to be around 13 billion years old, placing their formation close to the birth of the universe itself. These ancient stars serve as a cosmic clock, helping to measure the passage of time and providing a tangible connection to the early universe. Through the study of these stars, we can piece together a timeline of the universe's evolution, from the Big Bang to the present day. In addition to their role in galactic and stellar evolution, population 2 stars also provide important information about the nature of dark matter. As we mentioned earlier, dark matter is an invisible substance that makes up most of the mass in galaxies. Though we can't observe dark matter directly, we can infer its presence by studying its gravitational effects on visible matter, such as stars and gas. Population 2 stars, located in the outer regions of galaxies where dark matter is thought to be more abundant, are particularly useful for studying the distribution of dark matter. By analyzing the motion and distribution of these stars, astronomers can gain insights into how dark matter affects the formation and evolution of galaxies. Another exciting avenue of research involves the study of population 2 stars in other galaxies. Although much of our understanding of these stars has come from our own galaxy, the Milky Way, astronomers are increasingly able to observe population 2 stars in other, more distant galaxies. These observations provide a broader perspective on the role that population 2 stars play in the evolution of galaxies. By studying population 2 stars in a variety of galaxies, scientists can compare and contrast the formation and evolution of different galactic systems, gaining insights into the processes that govern galactic growth across the universe. The study of population 2 stars also ties into the broader quest to understand the origin of life in the universe. As we've seen, these stars were the precursors to later generations of stars that produced the heavy elements necessary for life. By examining these stars and their chemical makeup, astronomers can trace the origins of these life-essential elements and explore how they were distributed across the universe. This line of inquiry is central to the search for habitable planets and the broader question of whether life exists elsewhere in the cosmos. The knowledge gleaned from population 2 stars, therefore, not only informs our understanding of galactic evolution but also shapes our search for life beyond Earth. Looking ahead, the continued study of population 2 stars will undoubtedly lead to new discoveries and breakthroughs in our understanding of the universe. The next generation of telescopes and space observatories will provide even more detailed observations of these ancient stars, allowing us to explore their properties and environments in greater detail. With each new discovery, we inch closer to unlocking the secrets of the early universe and the processes that led to the formation of galaxies, stars, and life. The role of population II stars in galactic evolution is far-reaching and profound. From their chemical contributions to the formation of later generations of stars and planets to their importance in shaping the structure of galaxies and the distribution of dark matter, these stars have been central to the evolution of the universe. By studying them, we gain not only a deeper understanding of the cosmos but also insights into the processes that have shaped our own existence. These ancient stars are a vital piece of the puzzle, and their study will continue to yield new and exciting revelations for years to come. Through their legacy, population II stars help us to understand where we came from and where the universe may be headed in the future. As we continue to explore the role of population II stars in galactic evolution, it becomes clear that these stars have not only played a vital part in shaping the cosmos but also provide an unparalleled window into the deep history of the universe. Their study has become one of the most compelling areas of research in modern astrophysics, offering critical insights into both the nature of the universe and the processes that led to the formation of the galaxies we see today. One of the most profound implications of the study of population II stars is the understanding of how galaxies themselves evolve over time. As these ancient stars formed, they did so in the early stages of galactic development. These first generations of stars are typically found in the outer halos of galaxies, where they reside far from the bustling centers. Over time, these stars began to interact with their surroundings, contributing to the ongoing process of galactic formation. In the early universe, galaxies were not the grand spiral or elliptical shapes we see today. Instead, they were far more chaotic in structure, and their growth was driven primarily by the merging of smaller proto-galaxies. As these mergers took place, the population II stars within the merging galaxies were integrated into the newly forming galactic systems, further shaping their structure. This process of galactic merger and evolution was essential for the formation of larger, more complex galaxies that would later contain the stars and planetary systems capable of supporting life. Interestingly, population II stars not only provide a glimpse into the distant past of galactic formation, but they also continue to play a role in shaping the future evolution of galaxies. While most population II stars are now in their final stages of life, their remnants, such as white dwarfs and neutron stars, continue to influence the environment around them. These remnants can provide the raw material for future star formation, ensuring that the cycle of stellar birth and death continues unabated. In this sense, the legacy of population II stars is not limited to their time of formation but extends into the far future, as their remnants continue to contribute to the ongoing evolution of galaxies. Another significant aspect of the study of population II stars is their connection to the broader field of cosmology. By examining these stars, astronomers can gather valuable data about the age of the universe, its rate of expansion, and the processes that have shaped it over time. The oldest known population II stars are thought to be around 13 billion years old, and their study provides one of the most accurate methods for determining the age of the universe itself. By comparing the ages of these stars with other cosmic objects, scientists can refine their models of the universe's history and better understand its future trajectory. The study of population II stars is also crucial for our understanding of the formation and distribution of the elements throughout the universe. As we've already seen, these stars played a pivotal role in the synthesis of heavy elements, which are essential for the formation of planets, life, and the development of complex structures within galaxies. However, the process of stellar nucleosynthesis, the creation of these heavy elements in the cores of stars, is not as simple as it might seem. It involves intricate nuclear reactions that take place over billions of years, and the elements produced are released into space when stars die, enriching the interstellar medium. One of the key contributions of population II stars to the universe's chemical evolution is their role in the production of elements like carbon, oxygen, and iron. These elements are not only important for the formation of stars and planets, but also for the development of life itself. Without the heavy elements produced by population II stars, the universe would be a very different place. The elements required for life as we know it would simply not exist, and the possibility of life elsewhere in the universe would be vastly diminished. In this sense, population 2 stars were essential for the very conditions that made life possible. Moreover, population 2 stars also provide valuable insights into the formation of globular clusters, which are dense collections of old stars found in the halos of galaxies. These clusters are often home to large populations of population 2 stars, and their study can reveal much about the processes that led to their formation. Globular clusters are thought to be among the oldest structures in the universe, and by studying the population 2 stars within them, astronomers can gain a better understanding of the earliest stages of galactic evolution. These ancient star clusters serve as natural laboratories for studying the interactions between stars, gas, and dark matter in the early universe. Another intriguing aspect of population 2 stars is their potential to reveal information about the elusive population 3 stars, the first generation of stars to form after the Big Bang. Population 3 stars were massive, short-lived, and composed almost entirely of hydrogen and helium, with very little heavy elements. Although no population 3 stars have been directly observed, their existence is inferred from the properties of population 2 stars and other cosmic phenomena. By studying population 2 stars, scientists can gain indirect insights into the characteristics of population 3 stars and how they contributed to the formation of the elements that later formed population 2 stars. As we move forward in our study of these ancient stars, astronomers are employing increasingly advanced technologies to observe and analyze their properties. Telescopes like the James Webb Space Telescope, set to launch in the near future, will provide unprecedented views of the distant universe, allowing scientists to study population 2 stars in even greater detail. This new generation of telescopes will enable astronomers to peer deeper into the past, observing the earliest stages of star and galaxy formation. As a result, we can expect to learn much more about the role of population 2 stars in shaping the cosmos. Additionally, the study of population 2 stars is also opening up new avenues for research into the nature of dark matter and dark energy. While dark matter itself remains elusive, its presence is inferred from the gravitational effects it has on visible matter, such as stars and galaxies. By studying the motions of population 2 stars in the outer regions of galaxies, astronomers can gain insights into the distribution of dark matter and how it has influenced the formation and evolution of galaxies. Similarly, dark energy, the mysterious force responsible for the accelerated expansion of the universe, may also have had an impact on the formation and behavior of these ancient stars. Understanding how dark matter and dark energy interact with the stars and galaxies of the early universe is a key area of ongoing research, and population 2 stars offer a valuable perspective on this cosmic puzzle. The role of population 2 stars in galactic evolution cannot be overstated. These ancient stars were not only the first to form after the Big Bang but also played a crucial role in the enrichment of the universe with the heavy elements necessary for the formation of planets and life. Their contributions to the cosmic landscape are still being felt today, as their remnants continue to influence the formation and evolution of galaxies. By studying these stars, astronomers are able to piece together the history of the universe and gain valuable insights into the processes that have shaped the cosmos. The study of population 2 stars is not just about understanding the past, it is about unlocking the secrets of the universe and our place within it. The continued exploration of population 2 stars and their significance in galactic evolution reveals a much more profound connection between the evolution of these stars and the structure of the universe itself. By delving deeper into their history, we start to understand not just the past but also the mechanisms that are at play in shaping the universe, from the smallest stars to the largest cosmic structures. The ongoing study of these ancient stars is not just an academic pursuit but a way to understand the very nature of time, matter, and space itself. One area where the study of population 2 stars has profound implications is in our understanding of stellar evolution. These stars, while ancient and often in their dying stages, provide a fascinating window into the life cycles of stars. As previously mentioned, population 2 stars are thought to be low-metallicity stars, meaning they were formed with fewer heavy elements than modern stars like our Sun. This makes them closer to the first generation of stars that formed in the universe, which were primarily composed of hydrogen and helium. Understanding their evolution helps scientists make inferences about the properties of the first stars, known as population 3 stars, and how they eventually gave birth to the heavier elements that populate the universe today. When population 2 stars reach the end of their lives, they undergo significant transformations. Some may evolve into white dwarfs, while others may undergo supernova explosions, contributing even further to the enrichment of the universe. These processes release heavier elements into the interstellar medium, helping to seed the next generations of stars, planets, and even life. It's through these explosions and processes that the universe is continuously enriched, forming a cycle of creation and destruction that is essential for galactic evolution. The remnants of these population 2 stars often give rise to some of the most intriguing features in the universe, such as neutron stars and black holes. Neutron stars, the dense cores left behind by massive stars that undergo supernovae, offer unique opportunities to study extreme physics. These stars are incredibly dense, with a mass greater than the Sun packed into a sphere only a few kilometers across. The gravitational forces at play around neutron stars are so intense that they warp spacetime itself, providing an unprecedented laboratory for testing theories of gravity and relativity. On the other hand, black holes, particularly those that form from the remnants of massive population 2 stars, offer a powerful mechanism for studying the nature of the universe. Black holes are regions of spacetime where gravity is so strong that not even light can escape. Their study has profound implications not only for our understanding of astrophysics but also for fundamental physics. The study of the way black holes interact with their surroundings and how they evolve over time is opening up new avenues in our understanding of space and time. Population 2 stars also provide valuable information on the dynamics of galactic halos. These stars are predominantly found in the outer regions of galaxies, particularly in the halos that surround the galactic disk. By studying their motion and distribution, astronomers can gain important insights into the structure and composition of galactic halos, which are often dominated by dark matter. The movements of these stars, as well as their interactions with each other and the gas and dust in the galactic halo, give astronomers clues about the unseen forces at work in the universe. This information is crucial for understanding the role that dark matter plays in shaping galaxies and the larger cosmic structure. Furthermore, the study of these stars also provides vital clues about the process of galaxy formation. In the early universe, galaxies were not as well structured as they are today. They were often irregular in shape, and the stars within them were scattered in less cohesive patterns. Over time, these galaxies began to merge and evolve, and as they did, the population 2 stars within them played a crucial role in the formation of the galactic structures we see today. Their placement in the galactic halos is not coincidental. It tells a story of the dynamic processes that led to the formation of the first true galaxies that would later serve as the foundation for the more complex and diverse structures we see today. In addition to their role in galactic evolution, population 2 stars also contribute to our understanding of the larger structure of the universe. The universe itself is not just a collection of stars and galaxies, but rather a vast and intricate web of matter and energy. This cosmic web consists of filaments of gas and dark matter, with galaxies and clusters of galaxies distributed along these structures. Population 2 stars, as part of this cosmic web, provide valuable data for mapping out the large-scale structure of the universe. Their positions, motions, and interactions with their environment help astronomers trace the distribution of matter throughout the cosmos, allowing us to create a more accurate picture of the universe's evolution. As we learn more about the role of population 2 stars, we also uncover new information about the origins of the Milky Way galaxy itself. The Milky Way is thought to have formed through the merger of smaller protogalaxies, many of which contain population 2 stars. By studying these stars, astronomers can trace the history of the Milky Way's formation and better understand the processes that led to the development of our galaxy. The interactions between these stars and the galactic gas, as well as their role in shaping the galaxy's structure, provide crucial insights into how galaxies like the Milky Way came to be. One of the most significant breakthroughs in the study of population 2 stars is the increasing ability to study them in greater detail. The development of more advanced telescopes, such as the upcoming James Webb Space Telescope, is expected to revolutionize our understanding of these ancient stars. The James Webb Space Telescope will be capable of observing stars and galaxies billions of light-years away, offering unprecedented views of the early universe. This will allow astronomers to study population 2 stars in far more detail than ever before, providing deeper insights into their role in galactic evolution. As we continue to study these stars, new technologies and techniques will undoubtedly lead to even more discoveries about their nature and significance. For instance, the ability to study the light emitted by these stars and analyze their chemical composition provides a wealth of information about the early universe. By examining the spectra of population 2 stars, astronomers can determine the precise elements present in their atmospheres, revealing much about the conditions that existed when these stars formed. This kind of detailed analysis will allow us to piece together an even more accurate history of the universe and its evolution over time. Moreover, the study of population 2 stars also has implications for the search for life beyond Earth. The heavy elements produced by these ancient stars are essential for the formation of planets and the development of life as we know it. By studying these stars, we gain a deeper understanding of how the building blocks for life were scattered throughout the universe, paving the way for the formation of planets that might one day harbor life. This knowledge could inform future efforts to search for habitable planets in distant star systems, offering hope that we are not alone in the cosmos. As we move forward in our exploration of the universe, the role of population 2 stars will remain an essential part of the story. These stars, while long past their prime, continue to serve as beacons of the past, guiding us through the cosmic history that led to the present moment. Their study offers a glimpse into the very fabric of the universe, revealing the processes that have shaped not only the stars themselves but the galaxies and structures that define the cosmos. The significance of population 2 stars is far greater than just their contribution to the formation of galaxies or the enrichment of the universe with heavy elements. They are, in many ways, the cosmic messengers of time, carrying within them the story of the universe's earliest years. As we continue to unlock their secrets, we are not only learning about the past but also about the future, as the legacy of these ancient stars continues to shape the cosmos for billions of years to come. As we continue to unravel the significance of population 2 stars, it's important to highlight how their study touches on fundamental questions in astrophysics and cosmology. These stars, though ancient, are part of a larger puzzle that extends across all aspects of the universe's past, present, and future. Their role is integral not only in the context of galactic evolution, but also in helping to refine our understanding of the physical processes that govern the cosmos. Population 2 stars represent the early generations of stellar life, and their existence raises important questions about the nature of the universe's first few 100 million years. These stars, which formed from the primordial gas that was left behind after the Big Bang, are often referred to as the second generation of stars. They contain far fewer heavy elements compared to more modern stars like the Sun, which are classified as population 1 stars. The reason for this difference is that these early stars formed before the first supernovae, which are responsible for enriching the interstellar medium with heavier elements like carbon, oxygen, and iron. However, despite their relative lack of heavy elements, population 2 stars still played a significant role in shaping the universe as we know it. The heavy elements that are now present throughout the universe, including those that make up planets, life, and everything in between, came from the deaths of these ancient stars. The process by which these elements were created and spread across space is a key part of understanding the universe's chemical evolution. Every time one of these stars reaches the end of its life and explodes in a supernova, it releases these heavy elements into the interstellar medium, where they become the building blocks for new stars, planets, and even life itself. This ongoing cycle of stellar birth, death, and rebirth is a fundamental feature of galactic evolution, and population 2 stars were among the first to start this cycle. Their formation and eventual death enriched the universe with elements like carbon, nitrogen, and oxygen, elements that are necessary for the formation of planets and life. The chemical makeup of the universe has evolved significantly since the formation of these stars, and population 2 stars serve as a reminder of how far we have come in understanding the universe's complex chemistry. One of the most remarkable aspects of population 2 stars is the way in which they reveal the conditions of the early universe. By studying these ancient stars, we can learn more about the primordial gas clouds from which they formed, providing a glimpse into the state of the universe just a few 100 million years after the Big Bang. These stars were born when the universe was still relatively young, and their study helps to fill in the gaps of our understanding about the conditions that prevailed during the universe's infancy. The study of population 2 stars has also provided valuable insights into the evolution of galaxies. These stars are often found in the outer halos of galaxies, where they trace the history of the galaxy's formation and evolution. By studying their distribution, astronomers have been able to learn more about how galaxies like the Milky Way came to be. It's thought that in the early stages of the universe, galaxies were much smaller and less structured than they are today. Through the merger and accretion of smaller galaxies, larger structures began to form. Population 2 stars are remnants of this early galactic history, and by studying their motion and distribution, scientists can reconstruct the processes that led to the formation of galaxies as we know them. A key feature of population 2 stars is that they are often found in the globular clusters that orbit galaxies. These dense, spherical clusters of stars are often composed primarily of population 2 stars, and their study offers further insights into the history of galaxy formation. These clusters are among the oldest known structures in the universe, and they act as a kind of cosmic fossil record. By studying the stars in these clusters, astronomers can learn about the environment in which they were born, as well as the processes that have shaped the evolution of their host galaxy. In addition to the formation of galaxies, population 2 stars also play a key role in the ongoing process of star formation. The heavy elements produced by these ancient stars are recycled into the interstellar medium, where they become part of the gas clouds that give birth to new generations of stars. This recycling process is a critical component of the cosmic cycle of birth, death, and rebirth that governs the evolution of galaxies and the universe as a whole. The study of population 2 stars helps us understand this cycle in greater detail, providing a framework for understanding how galaxies evolve over billions of years. Population 2 stars also offer important clues about the behavior of dark matter. As we mentioned earlier, these stars are often found in the halos of galaxies, which are regions thought to be dominated by dark matter. By studying the motions of population 2 stars in these halos, astronomers can gain insights into the distribution of dark matter in the universe. This is crucial for understanding the role that dark matter plays in galaxy formation and evolution. Dark matter is one of the most mysterious substances in the universe, and understanding its properties is one of the key challenges facing modern astrophysics. In recent years, advances in observational techniques have allowed astronomers to study population 2 stars with unprecedented precision. The development of high-resolution telescopes, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, has opened up new avenues for studying these ancient stars. These telescopes are capable of observing stars and galaxies billions of light-years away, allowing us to study population 2 stars in distant galaxies that formed early in the history of the universe. With these new tools, astronomers are able to probe the nature of these stars in more detail than ever before, shedding light on the processes that shaped the universe's earliest galaxies. The study of population 2 stars is not just about understanding the past, however. These stars are also key to understanding the future of our galaxy and the universe as a whole. By studying the way in which population 2 stars have evolved over time, we can make predictions about the future of the Milky Way and other galaxies. For example, by examining the life cycles of these stars, we can gain insights into the fate of the Sun and other stars in our galaxy. We can also learn more about the processes that will eventually lead to the end of the universe, as stars like our Sun eventually burn out and evolve into white dwarfs, neutron stars, or black holes. Population 2 stars are also significant for their role in the search for exoplanets. These ancient stars often reside in systems with planets that are billions of years old. The study of these planets can provide insights into the conditions that existed on Earth long before life began, helping us understand the early stages of planetary evolution. Furthermore, by studying exoplanets around population 2 stars, we can explore the possibility that life could exist on other planets with similar conditions. The discovery of life elsewhere in the universe remains one of the greatest scientific questions of our time, and population 2 stars offer a valuable clue in this quest. The fascinating thing about these ancient stars is that they are like cosmic time capsules. They hold within them the history of the universe, preserving information about the conditions that existed when the first galaxies began to form. By studying these stars, we can piece together the story of the universe's origins and its evolution over billions of years. We are able to connect the dots between the early universe and the present day, providing a deeper understanding of how the cosmos has changed over time. The role of population 2 stars in galactic evolution is a vital and ongoing area of research that holds the key to unlocking many of the mysteries of the universe. These stars have been present since the very beginning of cosmic history, and their study continues to provide insights into the formation of galaxies, the nature of dark matter, and the chemical evolution of the universe. As we continue to explore these ancient stars, we will uncover even more secrets about the universe's past and its future, allowing us to better understand our place in the cosmos and the forces that shape the universe. Population 2 stars are like the foundation stones of galactic evolution. Their legacy stretches far beyond their own existence. These stars set the stage for the complex and diverse array of stellar and galactic phenomena we observe today. They were the building blocks for the first complex structures in the universe, and understanding them provides us with an invaluable lens through which we can examine the grand timeline of the cosmos. The relationship between population 2 stars and the formation of heavier elements is particularly fascinating. While the first generation of stars, known as population 3 stars, formed out of nearly pure hydrogen and helium from the Big Bang, population 2 stars were born into a universe that had already begun to undergo a process of chemical enrichment. When population 3 stars exploded in supernovae, they left behind a mix of elements that were essential for later generations of stars and galaxies. These second-generation stars, with their slightly higher metallicity, were able to build on this new, chemical foundation, and helped shape the universe in increasingly intricate ways. These stars often played a pivotal role in the development of the first planetary systems. The metals that population 2 stars contributed to the interstellar medium gave rise to the conditions necessary for the formation of rocky planets, the building blocks of the planets that orbit stars like our own Sun today. Without these earlier generations of stars, the universe would have been a far more barren place, with fewer complex structures capable of supporting life as we know it. The fascinating thing about population 2 stars is that they often exhibit incredibly long lifespans. Unlike their younger counterparts, which burn through their fuel relatively quickly and undergo dramatic transformations, population 2 stars have had the time to evolve more slowly. This gives astronomers the chance to observe them at various stages in their life cycles, offering insight into the universe's early epochs and its long-term future. These stars are often found in the oldest and most stable parts of galaxies, such as the galactic halos or in globular clusters. The fact that many population 2 stars are still alive today, despite having formed billions of years ago, speaks volumes about the durability of the processes that govern the star's evolution. As we look more closely at these stars, we also see that they are often surrounded by mysterious phenomena that tell us even more about the history of the universe. One of these phenomena is the presence of peculiar chemical abundances in some of these stars. For example, some population 2 stars have been found to contain unusually high levels of certain elements, such as lithium, which should have been depleted in the early universe. The reasons behind these strange chemical signatures are still not entirely understood. They might indicate that the first supernovae that formed these stars were different from what we expect, or they could be the result of processes that took place within the stars themselves, influencing their chemical composition in surprising ways. Population 2 stars also serve as a critical point of comparison for more modern, metal-rich stars. By studying these ancient stars, astronomers can trace the evolution of stellar populations over billions of years. These older stars serve as a baseline, against which we can measure the changing chemical composition of the universe. As heavier elements like carbon, oxygen, and iron have been introduced into the cosmic mix, stars that form today, like our Sun, are far more enriched in these elements, This has profound implications for our understanding of life's potential beyond Earth. The presence of metals in a star's chemical makeup is essential for the formation of planets that can support life. Without the enrichment brought about by stars like Population 2, it's unlikely that our own planet could have formed in the way it did. The remnants of Population 2 stars, specifically white dwarfs, neutron stars, and black holes, also provide astronomers with clues about the end stages of stellar life. These remnants give us insight into the processes that govern the final stages of a star's life, which are crucial for understanding the fate of stars in the Milky Way and other galaxies. While many of these stars will end their lives in supernovae, a significant number of them will eventually transform into white dwarfs, which are incredibly dense, stable objects that can continue to exist for billions of years after their parent star has burned out. These objects serve as a sort of cosmic fossil, preserving the history of a star long after it has ceased to shine. By studying these remnants, scientists can gain valuable insights into the evolution of the universe's first galaxies and the long-term fate of stars. Globular clusters, which are dense collections of ancient stars, often contain large numbers of Population 2 stars. These clusters are among the oldest and most tightly bound structures in the universe, and they are key to understanding the formation and evolution of the first galaxies. The study of globular clusters allows astronomers to peer back into the early universe and unravel the mysteries of its formative years. These clusters are made up of stars that are typically around 10 to 13 billion years old, and many of them are predominantly composed of Population 2 stars. By examining the properties of these clusters, scientists can gain critical insights into the conditions that existed when the universe was still in its infancy. The fact that globular clusters contain so many Population 2 stars suggests that these stars formed in large groups, which implies that the early universe was much more turbulent and dense than it is today. This environment allowed for the rapid formation of stars, and perhaps even the formation of galaxies themselves. As these stars and clusters evolved, they would have interacted with one another, triggering processes that led to the formation of the larger structures we see in the universe today. The stars within these clusters serve as time capsules, preserving the chemical and physical conditions of the early universe for modern astronomers to study. Another fascinating aspect of Population 2 stars is their role in the large-scale structure of the universe. As these stars formed and went through their life cycles, they contributed to the overall evolution of galaxies. They helped shape the stellar populations within galaxies and played a crucial role in the processes that led to the formation of galaxies as complex systems. The interplay between these stars, their environments, and the dark matter that surrounds them ultimately led to the creation of the rich and diverse array of galaxies we see in the cosmos today. Over time, Population 2 stars began to merge into larger and more complex galactic structures. As these stars died and exploded in supernovae, they enriched the interstellar medium with heavier elements, which were later incorporated into the formation of new stars, planets, and even life. This process of stellar death and rebirth is at the heart of the ongoing cycle of galactic evolution. Population 2 stars acted as the first factories for the heavier elements, transforming the simple hydrogen and helium of the early universe into the more complex elements necessary for life and planetary formation. In many ways, the story of Population 2 stars is the story of the universe itself. These stars helped to seed the universe with the elements that would form the building blocks of everything we see today, from planets and stars to galaxies and life. By studying these stars, astronomers can trace the origins of the elements that make up the world around us and understand how the universe has evolved over billions of years. The legacy of Population 2 stars is written into the very fabric of the cosmos, and their role in galactic evolution cannot be overstated. As the universe continued to evolve, the role of Population 2 stars in shaping the cosmos became even more apparent. These stars not only enriched the universe with heavier elements, but they also helped to establish the basic conditions for the formation of complex structures. As we look at galaxies today, we can trace their origins back to the first generations of stars, and we see how these early stars helped to create the diverse range of galactic structures that exist now. From the elliptical galaxies, which are often dominated by older stars like Population 2, to the spiral galaxies with their more youthful, metal-rich populations, the fingerprints of these ancient stars are everywhere. The legacy of population 2 stars also extends to the study of dark matter and the large-scale structure of the universe. While dark matter itself cannot be directly observed, its presence can be inferred by studying the motion of stars within galaxies. As population 2 stars formed and evolved, they interacted with dark matter, influencing the distribution of stars and galaxies on the largest scales. By studying these ancient stars and their effects on the surrounding dark matter, astronomers are able to gain valuable insights into the nature of this mysterious substance, which remains one of the greatest unsolved mysteries of modern astrophysics. In recent years, advances in observational technology have allowed astronomers to peer deeper into the past than ever before. Telescopes like the Hubble Space Telescope, the James Webb Space Telescope, and the upcoming generations of observatories are providing unprecedented views of distant galaxies and stars. These observations are shedding new light on the role of population 2 stars in galactic evolution, allowing scientists to better understand how the first stars and galaxies formed and how the universe has evolved over time. These new discoveries are pushing the boundaries of our knowledge, revealing more and more about the early universe and the stars that helped shape it. As we continue to explore the cosmos, the role of population 2 stars in galactic evolution will remain a critical area of research. These ancient stars are not only key to understanding the origins of the universe but also to understanding the processes that led to the formation of galaxies, stars, and planets. By studying these stars and their remnants, astronomers can unlock the secrets of the past and gain a deeper understanding of the cosmic story that has been unfolding for billions of years. In the grand scheme of the universe, the population 2 stars may seem like mere specks in the vastness of space, but their impact on the cosmos is immeasurable. These stars are the cosmic architects, shaping the very fabric of the universe and leaving a legacy that will continue to influence the development of galaxies, stars, and planets for billions of years to come. As we look to the future of astronomical research, the study of these ancient stars will remain a cornerstone of our quest to understand the universe's past, present, and future. The study of population 2 stars is more than just a quest to understand the ancient past of the universe. It also holds profound implications for the future. These stars are not just remnants of a distant time, but active clues to how the cosmos has and will continue to evolve. The way these stars evolved, lived, and died has shaped the distribution of elements and the conditions that allowed for the formation of later generations of stars and planets. In this sense, population 2 stars are at the heart of the ongoing cosmic cycle, one that spans billions of years, and they provide insights that may be crucial for understanding not only the history of the universe but its future as well. As we delve deeper into the nature of these stars, we can also observe the unique properties they exhibit. Population 2 stars, while ancient, can sometimes exhibit peculiarities in their chemical compositions that provide fascinating insight into the complex processes that govern the early universe. Some of these stars, despite their age, have been found to contain very low amounts of heavy elements compared to younger stars. This is a reflection of their origins in a primordial universe, one that was still rich in hydrogen and helium but lacked the diverse array of elements that would come later. However, some population 2 stars have been discovered to have much higher levels of certain heavy elements than their counterparts, sparking interest in the possibility that the process of chemical enrichment during the universe's formative years was not as uniform as we once thought. These stars may have formed in environments where the first supernovae, triggered by population 3 stars, had already begun to mix these elements into the interstellar medium. Or, alternatively, they might have been the product of multiple generations of stars interacting in unique ways. This mystery is still being unraveled, with each new discovery helping to clarify the role of population 2 stars in this complex cosmic process. In addition to their chemical properties, population 2 stars also reveal intriguing aspects of stellar dynamics. Many of these stars are found in the outer regions of galaxies, in structures known as the galactic halo. These regions are thought to contain stars that were among the first to form in the early universe, and they hold crucial information about the processes that led to the assembly of galaxies. The stars in these halo regions are often older, less metal-rich, and more spread out than stars in the central parts of galaxies. This distribution hints at the formation history of galaxies, suggesting that they may have grown from the merger and accretion of smaller clumps of gas and stars, a process that would have involved many generations of stars, including population II stars. Galactic halos, in particular, are an area of intense study because they contain a large number of population II stars. These halos are thought to be remnants of the early universe, and by studying the stars within them, astronomers can learn more about how galaxies were built over time. These stars are also significant in the study of dark matter, as the motion of stars within galactic halos can be used to infer the distribution of dark matter, which makes up most of the mass in the universe. By understanding how population II stars are distributed in these halos, scientists can gain valuable insight into the gravitational effects of dark matter and its role in shaping the structure of galaxies. Another fascinating aspect of population II stars is their contribution to the study of cosmic chronology. As these stars are some of the oldest objects in the universe, they act as a cosmic clock, providing a way to measure the passage of time since the Big Bang. By carefully studying the age and composition of population II stars, astronomers can determine the time that has passed since the formation of the first galaxies and stars. This helps to establish a timeline of the universe's evolution, shedding light on the processes that led to the formation of the structures we see today. One of the most exciting implications of this research is its potential to expand our understanding of the origin of life itself. The elements produced by population II stars, such as carbon, oxygen, and nitrogen, are the very building blocks of life. Without these elements, the formation of planets capable of supporting life would have been impossible. As population II stars enriched the universe with these essential elements, they paved the way for the creation of more complex systems, including the stars, planets, and galaxies that would later host life. In this sense, the study of these ancient stars is intimately tied to our understanding of life's origins and the conditions necessary for its existence. As we continue to explore the universe and study the remnants of these early stars, we also gain valuable insight into the nature of star formation itself. Population II stars are often found in environments where star formation rates were much higher than they are today. These stars may have formed in large, dense clusters, where the conditions for star birth were extreme. Studying these environments can help us understand the mechanisms that govern star formation, both in the past and in the present day. It also allows us to compare the conditions that led to the formation of the earliest stars with the conditions we see today, offering clues about how the process of star birth has evolved over time. The death of population II stars also contributes to our understanding of stellar evolution. These stars often end their lives as white dwarfs, which are remnants of stars that have exhausted their nuclear fuel. White dwarfs are incredibly dense, with masses similar to that of the Sun but volumes comparable to that of Earth. The study of these objects is crucial for understanding the final stages of stellar evolution and the fate of stars like our own Sunday white dwarfs, which are abundant in population II stars, also offer a unique way to study the cooling history of stars. By measuring the temperature and brightness of white dwarfs, astronomers can estimate their age, providing further insights into the age and evolution of galaxies and the universe as a whole. Beyond just their individual contributions to the cosmic cycle, population II stars also play a key role in the broader context of galactic evolution. The early stars enriched the interstellar medium with heavier elements, which in turn contributed to the formation of new generations of stars and planets. As the universe matured, these stars set the stage for the birth of even more complex structures, including spiral galaxies, which are rich in gas and dust and capable of forming new stars. Population II stars were instrumental in transforming a universe that was initially composed of almost pure hydrogen and helium into the diverse, chemically enriched environment we observe today. As we delve deeper into the galactic evolution triggered by population II stars, it's crucial to examine the processes that occur when these ancient stars die. The legacy of these stars is written not only in the chemical makeup of the universe but also in the structures that form after their demise. The types of remnants they leave behind are just as important as their earlier contributions. Many of these stars end their lives in a violent fashion, but instead of merely disappearing into oblivion, they play a pivotal role in shaping the environment around them. A significant portion of population 2 stars ends their lives as white dwarfs, the remnants of stars that were not massive enough to go supernova. A white dwarf is an extremely dense stellar remnant, typically composed primarily of carbon and oxygen. White dwarfs have a profound impact on the surrounding space. Their presence means that the elements they were composed of are scattered into space, enriching the interstellar medium even further. This process is crucial because it contributes to the cosmic recycling process, where the death of stars leads to the creation of new stars and planets. In some cases, though, population 2 stars may be massive enough to undergo a more dramatic end, dying in a supernova explosion. These stars are a bit more unusual within this population but provide a critical component in the enrichment of the universe with heavy elements. A supernova is one of the most powerful events in the universe, releasing tremendous amounts of energy and dispersing heavy elements like iron, nickel, and even more exotic elements into space. This material is essential for the formation of later generations of stars and planetary systems. Even as these stars burn out, they set the stage for new galactic structures to form. The heavy elements they eject become the building blocks for new stars, planets, and possibly even life. This idea has led to an understanding that stars do not simply live and die in isolation. Instead, their existence is tied to the evolution of the universe itself. Each new generation of stars and galaxies is a product of the earlier star's death, with each cycle contributing to the ongoing transformation of the cosmos. The chemical enrichment of the universe during this process is a key concept. Population 2 stars, as we discussed earlier, have lower metallicity compared to later generations of stars. Their relatively pure composition of hydrogen and helium is a hallmark of the early universe, but they also set the stage for a cascade of events that allowed for the creation of more complex elements. As they died, the supernova explosions from more massive stars and the winds from others released heavier elements into the surrounding gas. This allowed later stars to form with a richer composition of heavier elements, such as carbon, oxygen, and nitrogen, which are necessary for the development of life as we know it. One of the most fascinating aspects of this process is how it directly ties into the formation of galaxies. Galaxies, in essence, are the long-term products of the life cycles of stars, and population 2 stars played an important role in shaping their structure. These stars were often part of the halo of galaxies, which contains older, metal-poor stars. The halo is an important part of the galactic architecture, offering crucial information about the galaxy's formation. By studying the population 2 stars in this region, astronomers can learn about the early stages of galaxy assembly, including the mergers of smaller proto-galaxies that ultimately formed the large galaxies we see today. The life and death of population 2 stars are also intertwined with the phenomena we observe today in the center of galaxies. At the heart of many galaxies lies a supermassive black hole, a region of space where gravity is so intense that nothing, not even light, can escape it. While black holes are known to be a feature of later generation galaxies, their origins trace back to these early stars and their contributions. The immense energy released by the stars in the process of their formation, evolution, and eventual death helped shape the conditions for the birth of these colossal black holes. As black holes continued to grow and consume gas and stars, they contributed to the shaping of the galaxy, ensuring that the processes driven by population 2 stars and their subsequent remnants would be recorded in the very structure of the galaxy itself. The research into population 2 stars also allows us to glimpse the conditions of the early universe, particularly during the epoch known as reionization. This period, which occurred around 500 to 1,000 million years after the Big Bang, marks the time when the universe transitioned from being opaque to transparent. Before this period, the universe was filled with a hot, dense plasma of electrons and protons, and light could not travel freely. However, as the first stars began to form, they emitted ultraviolet light, which ionized the surrounding gas, causing it to become transparent. Population 2 stars, as part of this early star formation, helped drive this transformation, marking a crucial phase in the evolution of the universe. Through the study of these stars, we can also look into the cosmic timeline and how different elements and structures were formed over time. population 2 stars provide the oldest clocks in the universe. By analyzing their chemical compositions, astronomers can determine their ages and, in turn, measure the time since the universe's inception. This process has been vital in refining our understanding of cosmology, providing a more accurate measure of the universe's age and the timing of various events, including the formation of galaxies and large-scale structures. In addition to their scientific value, the study of population 2 stars also touches on more philosophical questions about the nature of the universe. How did the first stars form, and what conditions were necessary for their existence? How did the death of these stars influence the formation of future generations of stars, and by extension, the planets and life forms that arose later? These questions are not merely academic. They speak to the broader question of why the universe is the way it is and how everything we see today has come to be. What makes population 2 stars especially intriguing is their connection to the broader structure of the universe. These stars are not isolated phenomena. Rather, they are part of a larger cosmic cycle that is still unfolding. The remnants of these stars, whether in the form of white dwarfs, supernovae, or black holes, continue to shape the universe in ways we are only beginning to understand. The elements they produced are incorporated into the formation of new stars, planets, and even life. Their death and subsequent contribution to the interstellar medium ensure that the process of star formation is an ongoing cycle, one that spans billions of years and shows no signs of stopping. Ultimately, the role of population 2 stars in galactic evolution highlights the interconnectedness of all cosmic processes. The first stars may have been born in isolation, but their influence continues to ripple across the universe. The lessons they have taught us are not just about the past, they are about the ongoing evolution of the cosmos, and the future that awaits us. As we continue to study these ancient stars, we gain not only a deeper understanding of the universe's history but also valuable insight into the forces that will shape its future. The study of population 2 stars continues to offer new insights into the evolution of galaxies and the broader universe. As we look further into the intricate ways in which these stars influence the cosmos, we begin to understand that their contributions were not limited to merely the creation of elements, but also extended to the formation of cosmic structures. These stars played a role in the birth of the very galaxies we observe today. The birth of galaxies is intimately linked to the death of stars. After population 2 stars completed their life cycles, their remnants, along with the heavy elements they produced, mixed with the surrounding gas clouds. This process provided the raw material for the formation of new stars. The interstellar medium, composed of gas and dust, became increasingly enriched in elements like carbon, oxygen, and nitrogen. This enrichment laid the foundation for the next generation of stars and planets, which would eventually give rise to the rich diversity of celestial bodies we observe today. One of the key concepts in this process is the idea of stellar nucleosynthesis. This refers to the process by which stars create the elements found in the universe. In the early stages, population 2 stars were primarily composed of hydrogen and helium. However, as they lived and died, these stars fused lighter elements into heavier ones through nuclear reactions in their cores. The heavier elements produced during their lifetimes were expelled into space during their deaths, enriching the interstellar medium and allowing for the formation of subsequent generations of stars. This process occurred repeatedly across millions and billions of years, shaping the chemical makeup of galaxies. The way in which these stars enriched the universe with heavier elements also has a profound effect on the planets that eventually formed. The presence of elements like carbon, oxygen, and nitrogen is essential for the formation of planets and, in some cases, life. These elements are the building blocks of organic molecules, which are the fundamental components of life. Without the enrichment of the interstellar medium by population 2 stars, the conditions necessary for the development of complex life would not have existed. Therefore, the legacy of these ancient stars extends far beyond the stars themselves, influencing the very possibility of life in the universe. The stars that formed from the material enriched by population 2 stars were also different in their chemical compositions. As the universe aged, the amount of heavy elements in the interstellar medium increased, giving rise to population 1 stars. These stars, which are much younger than their population 2 counterparts, contain higher concentrations of heavier elements. These metals are crucial for the formation of planets, and as such, population 1 stars are often associated with the creation of planetary systems, such as our own solar system. The transition from population 2 stars to population 1 stars represents a shift in the way galaxies evolve. Early galaxies were dominated by population 2 stars, which were metal poor and often existed in the outskirts of galaxies. Over time, as the interstellar medium became increasingly enriched by the death of these stars, newer generations of stars formed with higher metallicity. These younger stars are often found in the disk regions of galaxies, where the process of star formation is ongoing. As a result, the structure of galaxies also changed, with the central bulges composed of older stars and the outer disks populated by younger, more metal-rich stars. Population 2 stars, in their death, played a critical role in shaping the morphology of galaxies. In particular, they help form the halos of galaxies, regions populated by older, metal-poor stars. These halos are important because they provide clues about the early stages of galactic formation. By studying the population 2 stars in these halos, astronomers can learn more about the processes that led to the formation of galaxies in the first place. This can also help us understand the role that dark matter played in galaxy formation, as the distribution of stars in the halo can reveal the presence of dark matter in a galaxy's outer regions. Another intriguing aspect of population 2 stars is their role in the formation of globular clusters. Globular clusters are dense groups of stars that are typically older and metal-poor, and they are often associated with the halos of galaxies. These clusters are thought to be some of the oldest structures in the universe, and many of them contain a high proportion of population 2 stars. Studying these clusters can give us a glimpse into the early stages of galaxy formation, as they represent some of the first groups of stars to form after the Big Bang. They are essentially living fossils, preserving the chemical composition and properties of the early universe. As we explore these early stages of galaxy and star formation, we are also confronted with questions about the evolution of galaxies over time. How did the processes that began with population 2 stars lead to the formation of the galaxies we see today? How did galaxies evolve from small, irregular objects into the large, well-structured systems with spirals, elliptical shapes, and massive central black holes that dominate the modern universe? One key factor in this evolution is the role of galactic mergers. In the early universe, galaxies were much smaller and more numerous, and many of them merged together to form larger galaxies. These mergers played a crucial role in shaping the structure of the galaxies we observe today. As galaxies collided and merged, their stars and gas clouds interacted, triggering new waves of star formation and enriching the interstellar medium with even more heavy elements. These events also contributed to the formation of the supermassive black holes found at the centers of many galaxies. Over time, as galaxies continued to merge and evolve, the larger, more complex galaxies we see today took shape. The study of population 2 stars provides valuable information about these early mergers and the role they played in galactic evolution. By analyzing the chemical composition of population 2 stars, astronomers can determine the timing of these events and gain insight into the processes that shaped galaxies in their formative years. The study of globular clusters, which are often the remnants of these early mergers, can also reveal important clues about the way in which galaxies grew and evolved. One of the most exciting aspects of this research is the potential for discovering even older generations of stars, those that predate population 2 stars. These stars, which are thought to have formed during the first few 100 million years after the Big Bang, are extremely difficult to detect due to their faintness and rarity. However, astronomers are working on advanced techniques to detect and study these ancient stars, and their discovery would offer a glimpse into the earliest stages of the universe. These stars could provide crucial information about the conditions that existed in the very early universe, before the formation of population 2 stars, and help us understand how the first elements and stars came into being. As we move further into the future of astronomical research, the study of population 2 stars and their role in galactic evolution will continue to be a central area of investigation. These stars are not only important because of their own properties, but also because they provide a window into the history of the universe and the processes that shape the galaxies, stars, and planets we see today. Through ongoing observations and theoretical work, we are uncovering more and more about these ancient stars and their lasting impact on the cosmos. Their story is far from over, and as our understanding of the universe deepens, the legacy of population 2 stars will continue to illuminate the past, present, and future of galactic evolution. As we continue to explore the profound role population 2 stars played in shaping the universe, we dive deeper into the mechanisms that govern their life cycles and their ultimate contributions to galactic evolution. These stars, often referred to as ancient stars, offer a unique lens through which we can study the past and unravel the complexities of the cosmos. Understanding their composition, behavior, and impact allows us to not only learn about their own existence but also to comprehend the forces that drive the very evolution of galaxies themselves. To understand why population 2 stars were so influential, it is essential to revisit the characteristics that set them apart from younger stars, such as population 1 stars. These population 2 stars are typically older, with ages stretching back to the early universe, often surpassing 10 billion years. Unlike younger stars, which are rich in metals, elements heavier than hydrogen and helium, population 2 stars have very low metallicity. This makes them the key to understanding the first stages of galactic formation when the universe was largely composed of hydrogen and helium. The low metal content of population 2 stars is a direct result of the lack of earlier stellar generations that could have seeded the universe with heavier elements. As these stars evolved, they began to process these lighter elements through nuclear fusion in their cores, creating heavier elements such as carbon, oxygen, and iron. The final stages of their lives, especially in supernova explosions, propelled these elements back into the interstellar medium, thus enriching the universe with the building blocks of future generations of stars, planets, and potentially life itself. This process of chemical enrichment is vital for understanding the timeline of galactic evolution. In the early stages, the universe was a sterile, inhospitable place, with only hydrogen and helium present. Over time, however, the death of population 2 stars, particularly through supernovae, began to alter the composition of the cosmos. The shockwaves from these explosions dispersed heavy elements into the surrounding gas clouds, allowing the formation of new generations of stars that were richer in these essential elements. The chemical evolution of the universe, however, did not happen in isolation. As population 2 stars died and seeded the universe with heavy elements, the structure of the universe itself began to change. The formation of galaxies became more efficient as heavier elements contributed to the cooling and condensation of gas clouds, making it easier for new stars to form. The interstellar medium became progressively enriched with elements like carbon, nitrogen, and oxygen, vital components for the formation of complex structures, including planetary systems. Population 2 stars also played an important role in shaping the formation of the early galaxies themselves. As we look at the structure of modern galaxies, we observe that they are composed of multiple components: the central bulge, the disk, and the halo. The population 2 stars are primarily found in the halo of galaxies, which is a relatively sparse region containing older, metal-poor stars. These stars were among the first to form in the universe and are scattered throughout the halo, offering astronomers an essential clue to the history of galactic formation. The existence of these stars in the halo is evidence of the primordial processes that led to the formation of galaxies. These stars were often born in smaller, isolated regions of the universe, which over time merged with other regions to form the galaxies we observe today. The material from these stars, enriched with heavier elements, eventually mixed with other gas clouds, triggering the formation of newer generations of stars. Over billions of years, the growth and evolution of galaxies led to the vast and diverse cosmic structures we see now. One of the most fascinating aspects of the contribution of population 2 stars to galactic evolution is their indirect influence on the formation of supermassive black holes. These black holes, which lie at the centers of most large galaxies, are thought to have formed early in the universe's history. Population 2 stars, through their life cycles and subsequent death, enriched the surrounding environments with elements that played a key role in the formation of these massive objects. As gas clouds collapsed under the influence of gravity, they could condense into dense cores that eventually formed the supermassive black holes observed today. The study of population II stars and their association with supermassive black holes reveals an important aspect of cosmic evolution: the connection between stellar life cycles and the formation of galactic structures. The metal enrichment provided by these stars allowed the creation of the first supermassive black holes, which in turn helped shape the galaxies around them. This symbiotic relationship between stars and black holes is crucial in understanding the dynamics of galaxy formation and evolution. The analysis of population II stars also sheds light on the early processes of star formation. These stars, which formed in the earliest stages of the universe, provide insight into how star formation occurred when the universe was still young and relatively simple. By studying the properties of population II stars, astronomers can learn about the conditions that existed in the early universe, including the density of gas clouds, the temperature of the surrounding environment, and the composition of the material from which stars formed. The low metallicity of population II stars also provides a unique opportunity to study the effects of metal-poor environments on star formation. Stars that form in metal-poor environments are believed to be different from those that form in metal-rich environments. For example, metal-poor stars may have different mass distributions and different internal structures, as the lack of heavier elements affects the way in which stars evolve and die. By studying the properties of population II stars, astronomers can gain insight into how star formation processes may have differed in the early universe compared to what we observe today. Moreover, the discovery and study of these ancient stars have led to the development of new theories in cosmology and astrophysics. One such theory is the idea of first stars, or population III stars, which are theorized to have formed shortly after the Big Bang. These stars, which are thought to be even older and more metal-poor than population II stars, are believed to be the very first stars to ignite in the universe. While no direct observations of population III stars have been made due to their faintness and distance, the study of population II stars gives astronomers valuable clues about the nature of these elusive stars. As technology advances, astronomers are able to study increasingly distant and faint objects, providing new insights into the evolution of the universe. Through the study of population II stars and their influence on galactic evolution, scientists are uncovering more about the early stages of the cosmos. As we continue to push the boundaries of our understanding, these stars will remain central to our exploration of the universe's origins and the complex processes that led to the formation of galaxies, stars, and planets. Population II stars are far more than just ancient celestial objects. Their role in galactic evolution is profound, as they were responsible for enriching the universe with the heavy elements needed for the creation of future stars, planets, and galaxies. Through their deaths, these stars transformed the cosmos, creating the conditions necessary for the formation of new stars and the evolution of galaxies. By studying these stars, astronomers gain valuable insights into the history of the universe and the processes that continue to shape the cosmos. As we continue to explore the depths of space, the legacy of population II stars will remain a central part of our understanding of the universe's evolution, shedding light on the past, present, and future of galactic formation. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.